Ancient stars hold secrets that defy the very age of the universe. We are exploring globular clusters, dense swarms of stars orbiting galaxies like cosmic beehives. By the end of this journey, you will know 50 strange discoveries that are reshaping modern astronomy. How can a star be older than the cosmos itself? What mysterious forces hide within these clusters? What cosmic story are you most curious to uncover? The first discovery strikes at the very foundation of everything we know. Astronomers using powerful telescopes like Hubble have found stars in globular clusters that appear to be older than the universe itself. This is not a small discrepancy. We calculate the age of the universe from the Big Bang to now to be around 13.8 billion years. Yet, the stellar evolution models used to date these ancient stars suggest some are over 14 billion years old. Think about that for a moment. How can something exist before the cosmos that contains it? It is a paradox that seems to defy logic. This forces a profound reconsideration of our cosmic timeline. Perhaps our measurements of the universe's age are subtly wrong. Maybe our understanding of how these ancient stars burn their fuel is incomplete. Or, and this is the truly thrilling possibility, there is a fundamental piece of physics, a force or an event that we have not yet discovered. This single strange finding reminds us that the universe is far more mysterious than we ever imagined. So how do we even know the age of a star billions of light years away? It is not as simple as checking a cosmic birth certificate. Astronomers rely on two powerful and elegant methods. The first is spectroscopy, which analyzes the starlight to reveal a star's chemical fingerprint. When you break that light apart, it tells a detailed story of the elements present. These ancient cluster stars are metal poor, meaning they contain very little besides hydrogen and helium. They are the universe's first generations, forged from the pristine gas of the early cosmos before heavier elements were common. The second method uses the Hertzsprung-Russell diagram, a kind of map that plots a star's brightness against its color. A star's position on this map reveals its stage of life, much like you can tell a person's age by their appearance and energy. By locating the point where the oldest stars begin to leave the main sequence, a stage called the main sequence turn-off, scientists can calculate their age with remarkable precision. And that calculation is what gives us numbers that challenge the age of the universe itself. To resolve this cosmic paradox, scientists are exploring two thrilling frontiers. One possibility is that our measurement of the universe's expansion rate, the Hubble constant, is slightly off. A faster expansion in the distant past would mean the universe is actually a bit older than we think, creating room for these ancient stars. The other, even more fascinating idea is that we are missing a piece of stellar physics. Perhaps these primordial stars burned their fuel in a different, more efficient way we do not yet understand, throwing off our age estimates. This is not just a small error, it is a sign that the fundamental rules governing stars may have a hidden chapter written only in the light of these ancient clusters. This stellar age paradox is not the only secret these ancient clusters keep. A second, equally strange discovery shattered a long-held assumption about their very nature. For decades, astronomers believed a globular cluster was a simple, pristine family. They thought all its stars were born at the same time from the same cloud of primordial gas, making them perfect cosmic fossils. But when they looked closer, the story became far more complex. They found that many clusters contain not one, but multiple distinct families of stars, each with its own chemical signature. This is the mystery of multiple stellar populations. The first generation of stars, as expected, are metal poor, composed almost entirely of hydrogen and helium. Yet, nestled among them are second and sometimes even third generations of stars. These younger stars show clear signs of being polluted with heavier elements like oxygen, sodium, and even aluminum. They are chemically enriched, so where did these new elements come from? The answer lies in the violent lives and deaths of the very first stars. The massive stars of that first generation did not fade away quietly. They lived fast and died young, exploding as colossal supernovas. These titanic blasts forged new, heavier elements in their cores and then scattered them back into the cluster's heart, seeding the surrounding gas with their stellar ashes. From this enriched debris, a second wave of stars was born. Think of it like a cosmic bakery. The first generation bakes a simple loaf of bread, using only the basic ingredients of flour and water, hydrogen and helium. Then they crumble that bread, mixing in fruits and nuts, the new heavy elements. From this richer dough, a second, more complex loaf is baked. This means these seemingly simple clusters are not static relics. They had a dynamic and perhaps violent inner life, with new stars igniting long after the first brilliant flash of creation. This forces us to completely rewrite their formation history. How could the cluster hold onto this enriched gas long enough for new stars to form, against the fierce stellar winds and radiation from its massive members? It is a puzzle that suggests these ancient beehives of stars are far more complex and resilient than we ever dreamed. The chemical differences between these stellar generations are not subtle. The second wave of stars shows a dramatic and baffling pattern. Their atmospheres are often depleted in oxygen and carbon, yet they are bizarrely enriched in sodium, nitrogen, and sometimes even aluminum. This is a very specific chemical fingerprint, one that points to a particular kind of nuclear cooking. These elements are forged at extremely high temperatures, far hotter than the cores of most stars. So what kind of cosmic oven could produce this strange recipe? One leading suspect is a type of very massive, fast-spinning star. These stellar behemoths, rotating so swiftly they are nearly flying apart, can churn their internal gases like a blender. This mixing brings the byproducts of hydrogen burning, where helium is created, to the surface, where fierce stellar winds can then blow this enriched material out into the cluster. Another possibility involves the dramatic interactions within binary star systems, where two stars orbit each other. In these close dances, one star can strip material from its companion, or they can both spill gas into a shared disk, creating a chaotic environment where unusual chemical processes can occur. But here lies the central mystery. How did the cluster manage to hold onto this newly forged material? The massive stars that produced these elements would have also unleashed devastating supernova explosions and powerful radiation. Such forces should have blasted all the gas clean out of the cluster, leaving nothing behind to form a second generation. The very event that creates the ingredients for new stars should also destroy the kitchen. Yet the second generation of stars exists. This means the cluster must have found a way to retain this precious, enriched gas. Perhaps the cluster was simply so massive, its gravity so immense, that it could hold on tight to the debris from those first explosions against all odds. Or maybe the second generation formed from the winds of those fast-spinning stars before the final, destructive supernovas went off, a brief window of creation in a chaotic environment. This ongoing debate reveals that these ancient clusters are not just simple collections of old stars. They are dynamic environments that somehow mastered a delicate cosmic balancing act, nurturing new life from the ashes of the old without tearing themselves apart in the process. The delicate chemistry of stellar generations is not the only force shaping these clusters from within. A far more powerful and invisible presence may be lurking in their very hearts. The third strange discovery points to the existence of a hidden monster, a gravitational anchor so strong it whips surrounding stars into a frenzied dance. Astronomers now have compelling evidence that some globular clusters contain intermediate mass black holes at their centers. For years, we only knew of two kinds of black holes. Stellar mass black holes, the remnants of collapsed giant stars weighing a few times our sun's mass, and the supermassive black holes, behemoths millions or even billions of times heavier than the Sun, which sit at the center of galaxies like our own Milky Way. But what existed in the vast gap between them was a cosmic mystery. Intermediate mass black holes with masses of hundreds to tens of thousands of suns were the missing link. Finding one is incredibly difficult as a black hole itself is invisible. You have to observe its effects on the things around it. Inside dense globular clusters, scientists using telescopes like the Chandra X-ray Observatory witnessed something extraordinary. They saw stars near the cluster's core moving at breathtaking, inexplicable speeds. These stars were orbiting something immense, something with a gravitational pull so fierce it could only be caused by a black hole of intermediate mass. Picture a handful of marbles whirling around an unseen drain at the bottom of a vast spinning bowl. The marbles are the stars, their speed telling you precisely how heavy that invisible central object must be. This is the primary method of detection, by tracking the rapid motion of these trapped stars. Sometimes the evidence comes from a brilliant flash of X-ray light, a final scream of energy as a star is torn apart and consumed by the black hole's immense gravity. The presence of these intermediate mass black holes solves one puzzle while creating several more. How did such an object form in a globular cluster? One theory suggests it started as a stellar mass black hole and grew over billions of years by relentlessly consuming gas and stars, or by merging with other smaller black holes in a chaotic gravitational waltz. Another, more dramatic idea is that it was born from the direct collapse of a single, impossibly massive star from the universe's first generation, a primordial giant we have never seen. If these black holes are common, they could be the very seeds from which the supermassive black holes at the centers of galaxies grew. A globular cluster with its intermediate mass black hole could have been swallowed whole by a young galaxy, its central black hole providing the foundational core for a future galactic titan. This means these ancient star clusters are not just cosmic fossils, but may have been the cradles for the most powerful objects in the universe. Detecting these invisible giants relies on reading the subtle language of gravity itself. Astronomers cannot see the black hole, so they must observe how it puppeteers the stars around it. The primary method involves measuring stellar velocity dispersion. This complex term simply means they track the speeds of many stars near the cluster's core. If the stars are all moving at roughly the same predictable pace, the central mass is likely spread out. But if their velocities are wildly different, with some stars whipping around at impossible speeds, it signals a massive, compact object is pulling the strings. It is the gravitational footprint of an invisible monster. Sometimes a more direct signal emerges. As gas and dust spiral into the black hole's accretion disk, they heat to millions of degrees, releasing powerful bursts of X-ray light. These flares are like a momentary beacon in the darkness, pinpointing the location of the intermediate mass black hole as it actively feeds. But such events are rare and fleeting, making them difficult to catch. The future of this search, however, holds even greater promise. Upcoming missions like the Laser Interferometer Space Antenna, or LISA, are designed to listen for the faintest ripples in space-time gravitational waves. When two intermediate mass black holes spiral into each other and merge, they would send a thunderous gravitational wave signal across the cosmos, one that LISA could potentially hear. This would not just confirm their existence, it would reveal their nature. The specific frequency and shape of these waves would tell us if the black hole was built slowly through mergers or born from a single, catastrophic collapse in the early universe. We are on the verge of not just seeing the shadow of these objects, but of hearing the very echoes of their creation. Finding planets in such a violent stellar environment defies all our expectations. Globular clusters are cosmic war zones where stars are packed so tightly that 1,000 could fill the space between our Sun and its nearest neighbor. In this chaotic dance, gravitational interactions are constant and fierce. and radiation from countless stars floods every corner. It is the last place you would expect to find the delicate, orderly systems of planets we know from our own galactic neighborhood. Yet they are there. The first confirmed planet in a globular cluster was discovered orbiting a pair of stars, a pulsar and a white dwarf, in the cluster known as Messier 4. This was not a gentle terrestrial world, but a survivor in an extreme system, proving that planet formation is a stubborn and universal process. The very existence of these worlds forces a complete rewrite of the rules. How could the protoplanetary disk of gas and dust, the cradle from which planets are born, possibly survive long enough to coalesce in such a hostile environment? The intense ultraviolet radiation from massive young stars should blast that delicate disk away in just a few million years, a blink of an eye on the cosmic timescale. The gravitational pull from a passing star could easily fling a fledgling planet out into the dark void of intergalactic space. For a planet to form and endure here, it must have either formed with astonishing speed, huddling incredibly close to its parent star for protection, or it must have been captured later in a rare, gentle gravitational exchange. This discovery shatters the notion that planets are exclusive to the quiet suburbs of galaxies. It suggests that even in the most crowded and dangerous urban centers of the cosmos, worlds can find a way. Imagine the view from the surface of such a planet. If life could somehow cling on there, the night sky would not be dark. It would be a permanent, brilliant daylight, lit by hundreds of stars as bright as our full moon, with no true night ever falling. The very concept of a solitary sun would be alien. This transforms globular clusters from simple collections of ancient stars into potential archipelagos of hidden worlds, each one a testament to the relentless and adaptable nature of cosmic creation. The planet found in Messier 4 is a testament to cosmic endurance, orbiting not a normal star but the stellar corpse of a pulsar. A pulsar is the incredibly dense, rapidly spinning core left behind after a massive star explodes in a supernova. This remnant is only about the size of a city, yet it possesses the mass of our entire sun, spinning hundreds of times per second and blasting out beams of intense radiation like a cosmic lighthouse. Any world existing in that environment is bathed in deadly levels of X-rays and gamma rays. For a planet to survive here, it had to endure an apocalypse. The very star it originally orbited was obliterated in a catastrophic blast that should have vaporized any nearby worlds. So how did this planet come to be? There are two leading theories, each more incredible than the last. One possibility is that the planet is a second-generation world born from the ashes. The supernova explosion that created the pulsar would have left behind a vast, expanding disk of metal-rich debris. From this chaotic cloud of stellar remains, a new, rocky world could have coalesced, a phoenix rising from the cosmic dust of its predecessor's death. The other theory suggests an even more dramatic history. This world may be an immigrant, a planet that originally formed around a different, quieter star. Through the complex gravitational dance within the dense cluster, it could have been stolen away and captured by the pulsar system, finding a new home in the most unlikely of places. Both scenarios highlight a stunning reality. Planetary formation is not a one-time event confined to calm stellar nurseries. It is a persistent, stubborn process that can occur even in the aftermath of stellar death, and planetary systems can be reshuffled and repurposed through cosmic interactions. The existence of such a world forces us to expand our definition of a habitable environment. While this particular planet is certainly a barren, irradiated rock, its very presence proves that planets can form and persist in conditions we once thought impossible. It opens a door to the idea that life itself, in forms we can scarcely imagine, might find a way in the most hostile corners of the universe, clinging to existence in the faint warmth of a dying star's embers. The stellar chaos within these clusters forges even stranger objects, stars that seem to cheat time itself. Among the ancient, cool red giants, astronomers spotted brilliant, hot blue stars burning with a youthful energy that should have faded billions of years ago. These are the blue stragglers, stellar anomalies that appear impossibly young compared to their ancient siblings. They are the vibrant blue jeans-wearing seniors in a retirement home full of white-haired residents, a sight that defies the natural order of stellar aging. How can a star remain so hot and bright long after its generation should have exhausted its fuel and begun to cool? The answer lies in the violent intimacy of the cluster environment. In the densely packed core, stars are not solitary beings. They live in close quarters, and dramatic encounters are inevitable. One leading theory is that of stellar collisions. Two older, slower stars, perhaps nudged by a passing gravitational influence, slam into one another in a cosmic merger. This catastrophic union mixes their hydrogen fuel, essentially hitting the reset button on their nuclear furnaces. The new combined star is more massive, hotter, and bluer than either of its progenitors, appearing reborn in a blaze of blue light. Another pathway involves a slower, more intimate dance within a binary star system. If two stars are locked in a close orbit, one star can siphon fresh hydrogen fuel from its companion. This stellar vampirism feeds the receiving star, reinvigorating its core and allowing it to burn brighter and hotter, effectively extending its prime while its donor companion is left as a stripped-down, faded remnant. These blue stragglers are not just cosmic curiosities. They are active laboratories, allowing us to witness the dramatic processes of stellar cannibalism and rebirth in real time. They show us that a star's life story is not always a solitary, predictable journey from birth to death. In the crowded heart of a globular cluster, a star can be granted a second act, its fate rewritten by a violent encounter or a cosmic partnership. This forces us to ask a profound question about our own place in the cosmos. Is our sun's quiet, solitary life the rule, or is it the exception in a universe where stellar lives are constantly being reshaped by their neighbors? Hubble's sharp eye has tracked these stellar anomalies, pinpointing their exact locations and brilliant blue light. On a specialized chart called a color magnitude diagram, which plots a star's color against its intrinsic brightness, blue stragglers stand out like brilliant sapphires misplaced in a field of rubies. They occupy a region where no star in a 13-billion-year-old cluster should logically remain, shining far brighter and hotter than their ancient neighbors. This precise mapping confirms they are not a trick of the light, but real, physical objects with a story to tell. Their positions within the clusters are also a vital clue. Many are found right in the densely packed cores where stellar traffic is heaviest and the chance for a cosmic fender bender is highest. This supports the dramatic collision model where two stars, nudged by a passing gravitational pull, spiral into a final, fiery embrace. The energy of such an impact is staggering, creating a single, rejuvenated star from the cosmic wreckage. But not all blue stragglers live in these urban centers. Some are found in the quieter outskirts of the cluster, a location that points toward the slower, more patient process of binary mass transfer. Here, in a stable dance, one star can gently siphon the lifeblood of hydrogen from its companion over millions of years, a cosmic parasite that grows younger as its partner grows old and faint. Hubble's data helps astronomers distinguish between these two birth scenarios, reading the subtle differences in their light and location to determine whether a specific blue straggler was born from a violent crash or a long, slow feast. These stars are not merely breaking the rules of stellar aging, they are actively rewriting them, showing us that a star's life path is not always a solitary journey. It can be radically altered by the company it keeps and the density of its neighborhood. These stellar rebirths are not the only force sculpting the cluster from within. A deeper, more pervasive mystery tugs at the very fabric of these systems, one that is defined by an absence rather than a presence. When astronomers measure the total mass of a globular cluster, they arrive at two very different numbers depending on how they look. The first method is to simply add up all the light from every star they can see. All that starlight translates directly into a mass of normal, luminous matter. The second method is to observe the cluster's gravity in action by tracking the orbital speeds of stars as they dance around the cluster's center. In almost every other large cosmic structure, from galaxies to galaxy clusters, these two numbers do not match. The dynamical mass, the one measured by gravity, is always vastly greater. That missing mass, the invisible glue that holds everything together, is what we call dark matter. But in globular clusters, something strange happens. The two numbers align almost perfectly. The mass in stars accounts for essentially all of the gravity we observe. There is no significant hidden reservoir of dark matter. This is profoundly puzzling. Galaxies are thought to be embedded within massive, diffuse halos of dark matter, which dictated their formation and now governs their rotation. It would be natural to assume that globular clusters, these dense satellites orbiting galaxies, would also be held together by their own small halos of this mysterious substance. Yet the evidence says they are not. They appear to be made almost entirely of the stars we can see. This suggests a fundamental difference in their origin story. Perhaps globular clusters did not form in isolation within vast dark matter clouds the way galaxies did. Instead, they may have been born directly from the collapse of giant, turbulent gas clouds within the early, developing galaxy itself. In this scenario, the gas was already stripped of or never contained a significant dark matter component. The cluster formed from pure baryonic matter, its incredible density alone providing the gravity to bind it together for billions of years. Or a more dramatic history may be at play. A globular cluster could have once possessed a dark matter halo, only to have it brutally stripped away during close encounters with its host galaxy or other clusters over eons. The cluster's stars, bound tightly together by their own mutual gravity, held fast while the more diffuse dark matter was pulled away into the galactic halo. This would make globular clusters the cosmic survivors, the dense, bony cores of systems that had their ethereal flesh torn away long ago. This missing dark matter is not just a minor detail. It forces us to see these clusters not as miniature galaxies, but as a completely distinct class of object. They are stellar cities built without the hidden framework that supports the galactic metropolises they orbit, raising a haunting question about the nature of the invisible stuff that makes up most of the universe's mass. Why did it abandon these ancient star swarms, and what does their pure, luminous nature reveal about the violent conditions of the early cosmos? The absence of dark matter in globular clusters sends a profound message about their origins. These ancient swarms of stars are not miniature galaxies, but something else entirely. Their pure, luminous nature suggests a different birth story, one that reaches back to the very dawn of cosmic structure. One compelling theory is that they were the universe's first major constructions. They may have formed incredibly early, condensing out of vast clouds of pristine hydrogen and helium gas before dark matter had even begun to collapse into the halos that would later cradle galaxies. In this view, globular clusters are the primordial building blocks, the foundational bricks that were later assembled into the grand spirals and ellipticals we see today. This would explain why they lack a dark matter component. They were forged from pure gas in a universe that was still simple and smooth. Another, more violent possibility is that they did once possess dark matter, but it was stolen from them. As a cluster orbits its host galaxy, it experiences relentless gravitational tides. The cluster's visible stars are packed so tightly they can resist this pull, but the dark matter halo, being far more diffuse, would be easily stripped away like fog scattering in a strong wind. The cluster we see today would be the surviving stellar core of a much larger but now vanished system. This distinction is critical for our models of cosmic evolution. If clusters formed without dark matter, it means the early universe could create massive, gravitationally bound structures through baryonic physics alone, a process we thought required dark matter's guiding hand. If they had it and lost it, then their current state is a testament to the brutal gravitational environment within galaxies, where only the densest objects can survive intact. Either way, these clusters are not passive fossils. They are active witnesses to the construction of the cosmos, their very composition holding the key to understanding how the first structures emerged from the formless dark. But even these dense stellar cities are not eternal. They are slowly, inexorably being dismantled by the immense gravity of their host galaxy. This process carves out one of the most beautiful and telling structures in the cosmos, tidal tails. These are long, graceful streams of stars, pulled like cosmic taffy from the cluster's main body as it swings around the galactic center. The cluster Palomar 5 is the textbook example. It appears not as a tight sphere, but as a faint, shimmering river of stars stretching for thousands of light years across the galactic halo. This is a snapshot of a cluster in its final act being unraveled before our eyes. The mechanism is a relentless gravitational tug of war. As the cluster orbits, the galaxy's pull is stronger on the side closest to the galactic center and weaker on the far side. This difference in force, the tidal force, stretches the cluster, pulling stars away from both ends. It is the same force that creates the ocean tides on Earth, but on a truly cosmic scale. These escaping stars do not just fly off randomly. They follow the cluster's orbit, forming delicate trails that map out the cluster's path through space. These streams are more than just a death knell. They are exquisite tools for science. By tracing their length and shape, astronomers can literally map the invisible gravitational field of the entire Milky Way. The stream acts like a cosmic probe, revealing the distribution of dark matter it passes through, showing us where the unseen mass of our galaxy is concentrated. The very thing that is destroying the cluster becomes a key to understanding the larger cosmos. The existence of these streams tells us that globular clusters have a life cycle. They are born, they evolve, and over billions of years, the galaxy's tides will completely disperse them, scattering their stars into the general population of the galactic halo. We are witnessing the slow-motion death of these ancient structures, a reminder that even the most enduring fixtures of the universe are subject to change, and that in their dissolution they offer one last brilliant gift of knowledge. These shimmering tidal tails are not just beautiful, they are a cosmic diagnostic tool. The European Space Agency's Gaia mission is revolutionizing this field, providing a three-dimensional map of over 1 billion stars in our galaxy with unprecedented precision. Gaia measures the positions, distances, and motions of stars with such accuracy that we can now trace the paths of individual stars as they are stripped from their parent clusters. It is like having a time-lapse video of the cluster's dissolution, frame by frame. By analyzing the exact trajectory and speed of stars within a tidal stream like that of Palomar 5, astronomers can perform a kind of cosmic forensics. The stream's shape, its density, and the velocities of its stars are all a direct response to the gravitational forces it has experienced. This allows scientists to map the gravitational potential of the Milky Way. That term simply means they can chart the landscape of our galaxy's gravity, revealing where mass is concentrated, both visible and invisible. A smooth, predictable stream suggests the cluster has orbited through a relatively uniform halo of dark matter. But if the stream shows kinks, gaps, or unusual twists, it is a sign of a recent close encounter with a smaller galaxy, a clump of dark matter, or another globular cluster. These gravitational scars are imprinted on the stellar river, telling a story of past collisions and near misses that would otherwise be completely invisible to us. Each disrupted cluster is therefore a historical record, its tidal tail a living timeline that chronicles the dynamic and often violent evolution of our galaxy's halo. We are not just watching clusters die, we are reading the autobiography of the Milky Way, written in the scattered light of its oldest stars. The quiet isolation of a single star is a rarity in the bustling downtown of a globular cluster. Here, stellar companionship is the norm, and these partnerships often evolve into the most bizarre and energetic relationships in the universe. Astronomers have catalogued a stunning variety of exotic binary systems where two stars or the remnants of stars are locked in a tight, intimate dance. These are not gentle waltzes, but frantic, whirling tangos that push the laws of physics to their absolute limits. Among the most extreme are millisecond pulsars. A pulsar is the rapidly spinning, city-sized core of a dead star, a neutron star that beams radiation like a lighthouse. Normally, they spin dozens of times per second. But a millisecond pulsar is a different beast entirely, rotating hundreds of times per second, its surface moving at a significant fraction of the speed of light. How does a dead star achieve such a dizzying spin rate? The answer lies in its binary partner. If the pulsar has a companion star, it can act as a cosmic vampire, using its immense gravity to siphon gas from its neighbor. This incoming gas doesn't just fall in, it spirals onto the pulsar's surface, transferring angular momentum and effectively spinning it up like a child's top being whipped faster and faster. The process is so efficient it can accelerate the pulsar to these incredible speeds, transforming a regular pulsar into a millisecond pulsar. This makes these systems perfect natural laboratories. The pulsar's spin is unbelievably stable, rivaling the precision of atomic clocks. By tracking the tiny variations in its rhythmic pulses, scientists can detect the most subtle effects of gravity, testing the predictions of Einstein's general relativity with a precision impossible to achieve on Earth. These binary dances create a space-time environment so warped that it allows us to listen for the faintest whispers of cosmic phenomena, from passing gravitational waves to the unseen tug of planets. Another class of exotic binary involves an even darker partner, a black hole. When a stellar mass black hole pairs with a normal star, it creates a system of terrifying beauty. The black hole's gravity is so strong it can pull a continuous stream of gas from its companion, forming a vast, hot, glowing disk of material called an accretion disk. As this gas spirals inward at nearly the speed of light, it heats to millions of degrees, emitting powerful bursts of X-rays that flicker and flare. These X-ray binaries are beacons of high-energy physics, allowing us to study matter in its most extreme state, under the influence of gravity so intense that not even light can escape. The very existence of these black hole binaries in clusters was a surprise. Theorists long thought that the same dynamical interactions that create them would also quickly kick them out, a gravitational slingshot effect ejecting the massive binary from the cluster. Finding them still there means the cluster's gravity is even more complex and retentive than we believed, capable of holding onto these cosmic predators. Each of these exotic systems, from the whirling pulsars to the voracious black holes, tells a story of survival and transformation in the most crowded neighborhood imaginable. They are not just celestial oddities, they are the ultimate test beds for the fundamental laws that govern our universe, proving that the most profound physics is often written in the violent, graceful dance between two cosmic partners. The precise timing of these cosmic dances offers a pathway to an entirely new sense, the ability to hear the universe. When two incredibly dense objects like neutron stars or black holes spiral inward in their final death embrace, they do not create a flash of light. Instead, they shake the very fabric of space-time, sending out ripples known as gravitational waves. These waves are the true language of these exotic binary systems, a silent symphony of gravity that we have only just begun to hear. Ground-based observatories like LIGO and Virgo are the instruments that listen for this cosmic music. Their incredibly sensitive lasers can detect a ripple in space-time smaller than the nucleus of an atom, a distortion caused by a cataclysm millions of light-years away. The mergers of stellar mass black holes and neutron stars are their primary targets, and globular clusters are cosmic factories for these very events. In the serene suburbs of the galaxy, where stars like our Sun live in quiet isolation, such violent unions are rare, but inside a globular cluster, the environment is a perfect storm for creating them. The density of stars is so immense that close encounters are a regular occurrence. A solitary black hole can gravitationally capture a passing neutron star, pulling it into a tight, fatal orbit. Two black holes, each the remnant of a massive star's death, can be nudged together by the gravitational pull of a third star, initiating a dance that will end in a merger billions of years later. These dynamical encounters, these cosmic introductions forced by proximity, are the engine that builds the binary systems that gravitational wave observatories detect. Think of a crowded ballroom where dancers are constantly being pushed together and swapped, creating new, unexpected pairs. The cluster is that ballroom, and the music is the relentless, silent force of gravity. Each merger detected is not just a confirmation of Einstein's theories. It is a direct message from the heart of these ancient stellar cities, telling us about the populations of dark remnants lurking within them. The specific masses of the merging objects, read from the gravitational wave signal, act as a fossil record. They reveal the types of massive stars that lived and died in the cluster's early history, and the complex gravitational interactions that have shaped their remnants over billions of years. With every chirp and ring of a gravitational wave event, we are auditing the invisible population of a globular cluster, learning about its dead without ever seeing their light. The stellar chemistry within these clusters holds a code we are only beginning to crack. Beyond the expected patterns of sodium and oxygen, astronomers have found bizarre chemical signatures that point to truly exotic events in the early universe. Some stars show puzzlingly high levels of lithium, an element that is notoriously fragile and easily destroyed in the nuclear furnaces of most stars. Finding it preserved in such ancient stars is like finding a perfectly intact fossil of a soap bubble, a delicate relic that should have vanished long ago. Its presence suggests these stars formed from gas that was never exposed to the extreme temperatures that would have burned this lithium away, hinting at a separate, cooler origin story for some of the cluster's material. Even more striking are the signatures of the rapid neutron capture process, or the R process. This is the cosmic mechanism responsible for creating the heaviest elements in the universe, like gold, platinum, and uranium. It requires an unimaginably intense flood of neutrons, an environment so extreme it can only occur in the most violent cosmic cataclysms. For decades, the prime suspect for the R process has been the merger of two neutron stars. When these incredibly dense corpses spiral together and collide, they can spray out clouds of neutron-rich material, seeding space with these heavy elements. Finding the distinct chemical fingerprint of R-process elements in globular cluster stars is a bombshell. It means that in the very first few 100 million years of a cluster's life, while its second generation of stars was still forming, neutron-star mergers were already happening. These titanic explosions were polluting the cluster's gas with gold and other rare elements, which were then incorporated into the new stars being born. The cluster had to be both dense enough to foster the binary interactions that lead to such mergers, and yet resilient enough to hold onto the precious, enriched debris they produced. This paints a picture of these ancient clusters not as serene retirement homes, but as vibrant, chaotic crucibles where the entire periodic table was being forged in a frantic, early burst of cosmic alchemy. The very stars we see today are the living records of those first, fleeting moments of creation and destruction, their light carrying the signature of events that shaped the chemical future of the entire cosmos. These ancient stellar chemistries are time capsules from the cosmic dawn. The specific ratios of elements we find in the oldest cluster stars are not random. They are the preserved chemical imprints of the very first supernova to ever illuminate the darkness. Each type of stellar explosion has a signature, a unique chemical recipe it scatters into space. A star that ends its life as a core collapse supernova, for instance, will produce a certain pattern of oxygen, magnesium, and silicon. When astronomers find a group of ancient stars all sharing that same distinct chemical pattern, it is like finding a fossil with a specific set of tooth marks. It tells you precisely what kind of predator was active in that environment. They are reading the last will and testament of stars that died over 13 billion years ago, recorded in the atmospheres of the stars that formed from their ashes. This allows us to reconstruct the conditions of those first star-forming regions. If the chemical fossils show a wide variety of patterns, it suggests the early cluster was seeded by many different supernovae, a turbulent and diverse beginning. But if the patterns are surprisingly uniform, it points to a more monolithic origin, perhaps dominated by a single, incredibly influential generation of giant stars. We can even estimate the masses of those first stars by the elements they left behind. The presence of certain heavy elements like europium points to very massive progenitors, stars that lived fast and died violently, while a different mix might suggest a population of smaller, longer-lived stars. It is a form of cosmic archaeology where instead of digging through layers of Earth, we split the light of ancient stars to uncover the history of the universe's first moments of structure and creation. This chemical record reveals that the cosmic dawn was not a gentle, uniform glow, but a stormy period of brilliant flashes, each one seeding the void with the raw materials for future worlds and ultimately for life itself. A new cosmic mystery arrives in bursts of radio energy so brief they last only 1,000th of a second. Fast radio bursts are among the most energetic and least understood phenomena in the universe, releasing more power in a millisecond than our sun does in 80 years. For years, their origins were a complete enigma, seeming to come from random points across the sky. But as astronomers pinpointed their locations with greater precision, a startling pattern emerged. Some of these incredibly powerful signals are not coming from deep in intergalactic space, but from much closer to home, originating within the halos of nearby galaxies. And the specific locations within those halos are eerily familiar. They trace back to environments that bear a striking resemblance to globular clusters. This is a profound clue. What could possibly exist inside an ancient cluster of stars that is capable of generating such a staggering, instantaneous release of energy? The leading suspects are the very exotic objects we now know thrive in these dense environments. A highly magnetized neutron star known as a magnetar is a prime candidate. Imagine the corpse of a massive star crushed into a city-sized ball, but possessing a magnetic field so intense it could erase a credit card from halfway across the solar system. If such an object were to undergo a starquake, a sudden crack in its rigid crust, it could unleash a titanic shockwave, converting that immense magnetic energy into a blistering flash of radio waves. Another possibility involves the chaotic dances of binary systems. A black hole or neutron star in a tight orbit with a companion star might sporadically pull off large chunks of material, causing a violent, bright accretion event that could power a burst. The dense core of a globular cluster provides the perfect breeding ground for these kinds of extreme objects and the dramatic interactions that could trigger them. The speculative link between fast radio bursts and globular clusters is a testament to how our view of these ancient systems has evolved. They are no longer seen as quiet backwaters, but as dynamic factories for the most energetic events in the cosmos. The next time a millisecond flash of radio energy streaks across the universe, it might just be a message from one of these stellar cities, a brief, brilliant scream from a monster born in the crowded dark. The sheer violence of a magnetar's birth could be the cosmic trigger for these fleeting radio screams. These neutron stars are forged in the most extreme environments imaginable, and globular clusters provide the perfect crucible. When two normal stars collide and merge in the cluster's dense core, the resulting cataclysm can create a newborn star with a ferociously powerful magnetic field, a magnetar. Alternatively, in a tight binary system, one neutron star could accrete so much mass from its companion that it collapses further, amplifying its magnetic field to magnetar strength in a process that defies simple explanation. The energy stored in a magnetar's magnetic field is almost incomprehensible. A single starquake, a sudden fracturing of its rigid crust, could release a vast portion of that pent-up energy in a single, explosive flash of radio waves, a signal we would detect as a fast radio burst. To confirm this connection, astronomers are racing to catch a fast radio burst in the act. The goal is to pinpoint one with such precision that it can be unquestionably linked to a specific globular cluster. If that cluster is then studied with X-ray telescopes and shows the telltale, persistent glow of a magnetar, the case would be virtually closed. We would have identified one of the universe's most powerful and mysterious signals with one of its most exotic stellar remnants. This would transform our understanding of these ancient clusters from quiet stellar retirement homes into active volcanoes, capable of sudden, brilliant eruptions that echo across the cosmos. The immense gravity of a globular cluster can warp the very space around it, creating a natural cosmic telescope. This phenomenon, called gravitational lensing, occurs when the cluster's collective mass bends the path of light from even more distant objects behind it. Imagine looking through the bottom of a wine glass at a distant street lamp and seeing its light distorted into a shimmering ring or arc. On a cosmic scale, that is precisely what happens when a globular cluster aligns with a background galaxy. The cluster's gravity acts as the lens, magnifying and twisting the galaxy's light into beautiful, luminous smears known as Einstein rings or arcs. But astronomers have found an even more subtle and telling use for this effect within the clusters themselves. They watch for brief, unpredictable flashes of a distant star as it suddenly brightens and then fades back to normal. This is a microlensing event. It happens when a dark, compact object within the cluster, like a solitary black hole or a neutron star, passes directly between our telescopes and a faraway background star. For a few days or weeks, the invisible object's gravity acts as a tiny lens, focusing the background star's light and causing it to temporarily flare. That flash is the only sign we get of the lens's presence. It is the ghostly signature of something massive, dark, and utterly unseen. Each microlensing event is a direct detection of the cluster's hidden population, a census of its dark remnants that emit no light of their own. By counting these fleeting events, scientists can estimate how many stellar corpses are drifting like invisible ghosts through the stellar swarm. The numbers are startling, suggesting that globular clusters may be teeming with thousands of these dark, compact objects, far more than we ever anticipated from simply counting shining stars. This hidden mass, previously invisible, could help explain the precise gravitational dynamics we observe in the cluster's core, the very same dynamics that hinted at intermediate mass black holes. It seems the darkness within these ancient star cities is alive with unseen, massive inhabitants, each one revealing itself only by the briefest distortion of a distant point of light. These microlensing surveys are a patient cosmic watch, scanning the same dense star fields for years. The Hubble Space Telescope, along with planet-hunting missions like Kepler, have been instrumental in this search. They do not stare at the clusters looking for bright objects. Instead, they monitor millions of individual stars for the telltale, temporary brightening that signals an unseen mass passing in front of one. It is a statistical game requiring immense amounts of data and precision. Each flash, each tiny spike in a star's light curve is a potential discovery. By analyzing the duration and shape of these microlensing events, astronomers can actually weigh the invisible object causing them. A brief, sharp flash points to a low-mass object, perhaps a small black hole or a neutron star. A longer, more drawn-out brightening suggests a much heavier lens, possibly an intermediate mass black hole drifting through the cluster's outskirts. This data is building a census of the dark, compact objects that have long been hidden from view. The preliminary results are staggering. They suggest that a globular cluster's population of stellar mass black holes could be in the thousands, a vast unseen army of dark remnants making up a significant fraction of the cluster's total mass. This hidden architecture solves an old puzzle about cluster stability. For decades, theorists argued that so many heavy black holes would dynamically heat the cluster, causing it to expand and evaporate stars too quickly. But new, sophisticated simulations show that these black holes can actually settle into a dark core, providing a gravitational scaffold that actually helps hold the entire cluster together over billions of years. The luminous stars we see are just the visible tip of a much deeper, darker iceberg. Beyond black holes and neutron stars, these surveys even probe the nature of dark matter itself. Could some of these brief lensing events be caused by exotic, compact clumps of dark matter, so-called massive astrophysical compact halo objects, or MACHO? While most dark matter is thought to be a diffuse sea of particles, the possibility remains that some of it could be tied up in primordial black holes or other dense objects. Every unexplained microlensing event is a data point, a clue that helps us constrain what the unseen majority of the universe is actually made of. Each flicker of a distant star is a vote in a cosmic election, helping us determine the true rulers of these ancient stellar cities. The cosmic zoo once had two distinct cages, one for star clusters and another for galaxies. That clean division has now collapsed with the discovery of ultra-compact dwarf galaxies. Initially mistaken for unusually large globular clusters, these objects are rewriting the definitions of cosmic structure. They appear as small, dense points of light, but when astronomers measured their masses and velocities, they found something impossible for a normal cluster: the gravitational signature of dark matter. A true globular cluster's gravity comes only from its stars, but these ultra-compact dwarfs are far heavier than their starlight can account for. They must be embedded within their own massive, invisible halos of dark matter, just like full-sized galaxies. This means they are not merely collections of stars, but the stripped-down cores of what were once much larger dwarf galaxies. Imagine a grand castle reduced by time and tied to its central, impenetrable keep, with its original, vast lands now invisible but still exerting their influence. That is the nature of an ultra-compact dwarf galaxy. It is a galactic fossil, a remnant of the violent construction of the universe, where smaller galaxies were cannibalized by larger ones, leaving only their dense hearts behind to orbit as cosmic imposters among the true globular clusters. This discovery blurs the line completely, forcing us to ask what truly defines a galaxy. Is it simply a question of scale, or is the presence of that invisible dark matter halo the true marker of a galaxy's soul? The story of an ultra-compact dwarf galaxy is a cosmic tale of survival against impossible odds. To understand how these dense, dark matter-rich objects form, we must journey back to the early universe, a time of chaotic construction. One of the most compelling theories is that of tidal stripping. Imagine a small but fully formed dwarf galaxy, complete with its own halo of dark matter and a sprawling population of stars. As it orbits a much larger galaxy, like our Milky Way, it passes too close. The immense gravitational tide of the larger galaxy acts like a cosmic cheese grater, relentlessly pulling and stretching the smaller one. The loosely bound outer stars and the diffused dark matter halo are the first to be stripped away, torn off into long, faint streams that eventually dissolve into the galactic halo. What remains is only the dwarf galaxy's incredibly dense central core, a region where the stars are so tightly packed that the larger galaxy's gravity cannot easily pry them loose. This surviving nugget, now orbiting as an ultra-compact dwarf, is all that is left of a once proud system. It is the celestial equivalent of a ship reduced to its hardened steel keel after a terrible storm, everything else swept away. This process explains their bizarre properties, their immense mass hidden within a small, starlit package, because they retain the dark matter from their original, larger halo, now compressed into a tiny volume. This violent origin story makes them more than just curiosities. They are living fossils that record the cannibalistic history of galaxy growth. Every ultra-compact dwarf we find is likely the ghost of a galaxy devoured, a testament to the predatory nature of cosmic evolution. But there is another, even more profound possibility for their birth. Some of these objects may not be the stripped cores of small galaxies, but the pristine remnants of the universe's very first building blocks. In the early cosmos, dark matter first collapsed into small clumps known as halos. Within these halos, the first stars ignited. The most massive and dense of these primordial clumps could have formed stars with such incredible efficiency that they used up nearly all their gas in one frantic burst, creating a single, ultra-dense stellar system from the very beginning. These objects would have been among the first structures to light up the darkness, and they would have naturally contained dark matter, as it was the gravitational foundation of everything. In this scenario, an ultra-compact dwarf is not a stripped-down relic, but a preserved pioneer, a cosmic seed that never grew into a larger galaxy. It has survived for billions of years essentially unchanged, a perfect snapshot of the universe's first steps toward structure. This dual identity, as both a stripped core and a primordial relic, is what makes them so vital to astronomy. By studying their numbers, their locations, and their detailed chemistry, we can piece together the assembly history of galaxies like our own. Are most of the ultra-compact dwarfs in a galaxy's halo the shredded remains of past mergers, telling a story of violent growth? Or do some of them represent the original, unassembled bricks, revealing the initial conditions of the cosmos itself? They force us to redraw the family tree of cosmic structures, blurring the line between a star cluster and a galaxy, and revealing a continuum of diversity in the universe's stellar cities. These brilliant, pulsating stars are the lighthouses of the cosmos, guiding us across the vast, empty gulfs between galaxies. Within the ancient confines of globular clusters, astronomers found a special class of stars whose rhythmic heartbeat provides one of the most reliable measuring sticks in the universe. These are the variable stars, and their predictable cycles of brightening and dimming hold the key to mapping the scale of everything we see. The most crucial for these clusters are the Lyrae stars, ancient pulsating giants that serve as standard candles. A standard candle is an object whose intrinsic brightness, its true luminosity, we can determine with confidence. Once we know how bright something truly is, we can compare that to how dim it appears from Earth. The difference between its real brightness and its apparent faintness gives us its distance with remarkable accuracy, the same way you could judge how far away a car is at night if you knew the true strength of its headlights. Lyrae stars are perfect for this role because their pulsation period, the time it takes to go from bright to dim and back again, is directly linked to their true luminosity. By simply measuring the rhythm of their light, we can know exactly how bright they are. When we find these stellar metronomes inside a globular cluster, we can pin down that cluster's distance from Earth with precision. This transforms the cluster from a mere collection of stars into a fundamental rung on the cosmic distance ladder, a critical step that allows us to calibrate measurements for objects far beyond our own galaxy. Without these pulsating beacons in globular clusters, our understanding of the universe's vast expanse would be built on a foundation of sand. Their steady, predictable light gives us the first, firm step from which we can reach out into the deepest cosmic dark. These stellar heartbeats once guided astronomers to our place in the cosmos. A century ago, Harlow Shapley used the rhythmic pulse of Lyrae stars within globular clusters to perform a feat of cosmic cartography that redefined humanity's address. By measuring the distances to these clusters scattered across the sky, he made a stunning realization. They were not centered on our solar system, but formed a great spherical halo around a distant point in the constellation Sagittarius. This was the true center of our Milky Way galaxy. We were not at the heart of our own universe, but living in the quiet suburbs, a discovery that humbled our perspective and forever changed astronomy. Shapley's map, drawn from the light of these ancient pulsating stars, was the first true outline of our galactic home. Today, that legacy is more vital than ever. Modern cosmology's greatest quest, measuring the precise rate of the universe's expansion, hinges on the same fundamental principle. The Hubble constant, the number that tells us how fast the cosmos is stretching, requires a rock-solid distance ladder, and its first rungs are still built in the hearts of globular clusters. Space telescopes like Hubble and Gaia rely on the unwavering light of Aurora Lyrae and other variable stars to calibrate distances to nearby galaxies. This local calibration then extends outward, step by step, to measure the far more distant supernova that reveal the universe's expansion speed. Any tiny error in that first crucial step, the distance to a globular cluster, propagates outward, creating uncertainty in our most fundamental cosmic measurement. The gentle, ancient pulse of these cluster stars is therefore not just a historical curiosity. It is the bedrock upon which we measure the fate and scale of everything, a steady drumbeat against which we listen for the accelerating rhythm of an expanding universe. Even the most placid-looking star swarm hides a hidden dance of astonishing complexity. For generations, astronomers assumed globular clusters were simple, relaxed systems, vast spheres of stars where every motion had smoothed into a state of perfect dynamical equilibrium over billions of years. They were thought to be cosmic retirement homes where stellar orbits were calm, random, and predictable. But when scientists began taking the precise radial velocities of thousands of individual stars within these clusters, they uncovered a reality far more strange and dynamic. They found that some of these ancient cities of stars possess hidden internal structures, like entire cores that are slowly rotating in unison, or vast streams of stars all moving in the same direction. This is the mystery of kinematic substructure, and it shatters the long-held assumption that these clusters are in a simple state of balance. Imagine a vast, swirling whirlpool hidden within what appears from a distance to be a perfectly still pond. That is the kind of secret these clusters have been keeping. The primary tool for this discovery is spectroscopy, which allows astronomers to measure whether a star is moving toward us or away from us by the subtle shift in its light. By mapping the radial velocities of countless stars, they can create a three-dimensional map of the cluster's internal motions. In a truly relaxed system, these motions would be random, like a swarm of bees with no collective direction. But in many clusters, the data reveals a different story. In the core of Omega Centauri, for instance, stars are not just buzzing randomly. They are all participating in a slow, majestic rotation, a ghostly carousel spinning in the deep. Other clusters show anisotropic velocity distributions, a technical term meaning the stars are not moving equally in all directions. They might be streaming preferentially along a specific axis, like commuters on a cosmic freeway, their motions aligned by some ancient, unseen hand. This presence of ordered motion is a profound clue. It tells us that the cluster has not fully erased the memory of its birth. These kinematic fingerprints are fossils of the cluster's formation. A rotating core suggests the cluster may have formed from a smaller, spinning cloud of gas that never completely lost its original angular momentum. The aligned streams of stars could be the lingering traces of smaller clusters that merged together long ago, their stellar populations not yet fully mixed into a homogeneous whole. The cluster is not a simple, featureless ball, but a palimpsest with the faint, ghostly writing of its violent youth still visible in the motions of its stars. This forces a major revision of our models. We can no longer treat these systems as perfectly relaxed and simple. their internal dynamics are far richer and more complex, shaped by a history of mergers, accretion, and a formation process that imprinted structures which have persisted for nearly the entire age of the universe. The very fact that we can still see these patterns today means the relaxation process is not as efficient as we thought, or that these clusters are constantly being stirred by some unseen force, perhaps the very same population of dark remnants that microlensing has begun to reveal. The quiet, ancient sphere is an illusion behind which lies a universe of hidden motion and a history written in velocity. These hidden streams and rotating cores are not just patterns, they are puzzles waiting to be solved. To decipher their meaning, astronomers turn from telescopes to supercomputers, constructing entire virtual universes to replay the life of a globular cluster. This is the science of dynamical modeling, where the laws of physics are coded into simulations that run for millions of computer hours. The goal is simple yet profound: to take a simulated cloud of primordial gas and watch it collapse, form stars, and evolve for 13 billion years, hoping that the final virtual cluster matches the strange kinematic features we see in the real ones. These simulations are like cosmic time machines, and they reveal that the ordered motions we detect are often the ghostly echoes of a violent past. A stream of stars all moving in the same direction could be the final, fading signature of a smaller cluster that was swallowed and digested long ago, its stars not yet fully mixed into the larger population. A slowly rotating core might be the lasting imprint of the original gas cloud spin, a fossilized whirlpool preserved from the moment of birth. But the simulations point to another, more active influence: the gravitational hand of an intermediate mass black hole. A black hole of this size can act like a massive shepherd, its immense gravity organizing the orbits of nearby stars, creating that distinct, rotating core we observe. Without this dark anchor, the simulations show, such ordered motion would often be smeared away by random encounters over billions of years. The black hole's persistent pull keeps the memory of that motion alive. The revolution in this field is being driven by data from the Gaia mission. Before Gaia, models were based on best guesses. Now they are constrained by hard, precise facts. Gaia provides the real-life starting positions and velocities for hundreds of thousands of stars within a cluster. Scientists can feed this exquisite data into their simulations and run them backward in time, like rewinding a cosmic film, to see what initial conditions naturally lead to the complex structures we see today. This allows them to test different scenarios with incredible precision. Was this cluster born from a single cloud, or was it built from a series of mergers? Does its core require a black hole to explain the stellar motions, or can it be explained by a dense population of stellar remnants? Gaia's data is the key that unlocks these questions, transforming dynamical modeling from an abstract exercise into a precise tool for historical reconstruction. We are no longer just guessing at the history of these ancient star cities. We are replaying their entire lives, frame by frame, guided by the real-world motions of their countless stellar citizens. This constant stellar traffic creates the perfect conditions for the most violent relationships in the cosmos. Within the bustling cores of these ancient clusters, astronomers have found a stunning abundance of X-ray binaries, systems where a dense stellar corpse, a neutron star or black hole, slowly devours its companion. The process is both beautiful and terrifying. In these tight orbits, the immense gravity of the compact object pulls a continuous stream of gas from the outer layers of its neighboring star. This stolen material does not fall straight in, but spirals down into a vast, hot disk that whips around the central object at nearly the speed of light. Friction within this accretion disk heats the gas to millions of degrees, causing it to glow with an intense, high-energy brilliance we detect as X-rays. Each of these systems is a beacon, a natural laboratory where we can observe the physics of extreme accretion in action. The sheer number of them in globular clusters is the key clue. In the calm galactic disk where our Sun resides, such binaries are rare. But in the cluster's dense core, close encounters are a regular occurrence, gravitationally pairing up neutron stars and black holes with new companions all the time. This means the population of X-ray binaries acts as a direct census of the hidden compact objects lurking within the cluster. By counting these brilliant X-ray lights, we are essentially taking a roll call of the stellar mass black holes and neutron stars that would otherwise be completely invisible to us. The specific properties of the X-ray emission tell an even deeper story. A steady, faint glow suggests a stable, long-term partnership where matter is flowing smoothly. But sudden, dramatic flares and burst signal moments of instability, perhaps when a clump of material crashes onto the neutron star's surface or when the accretion disk undergoes a violent reorganization. By decoding this flickering language of high-energy light, we learn not only about the populations of these dark remnants, but also about the fundamental behavior of matter under the most extreme gravitational stresses imaginable. This stellar traffic creates the perfect conditions for the most violent relationships in the cosmos. Within the bustling cores of these ancient clusters, astronomers have found a stunning abundance of X-ray binaries, systems where a dense stellar corpse, a neutron star or black hole, slowly devours its companion. The process is both beautiful and terrifying. In these tight orbits, the immense gravity of the compact object pulls a continuous stream of gas from the outer layers of its neighboring star. This stolen material does not fall straight in, but spirals down into a vast, hot disk that whips around the central object at nearly the speed of light. Friction within this accretion disk heats the gas to millions of degrees, causing it to glow with an intense, high-energy brilliance we detect as X-rays. Each of these systems is a beacon, a natural laboratory where we can observe the physics of extreme accretion in action. The sheer number of them in globular clusters is the key clue. In the calm galactic disk where our Sun resides, such binaries are rare, but in the cluster's dense core, close encounters are a regular occurrence, gravitationally pairing up neutron stars and black holes with new companions all the time. This means the population of X-ray binaries acts as a direct census of the hidden compact objects lurking within the cluster. By counting these brilliant X-ray lights, we are essentially taking a roll call of the stellar mass black holes and neutron stars that would otherwise be completely invisible to us. The specific properties of the X-ray emission tell an even deeper story. A steady, faint glow suggests a stable, long-term partnership where matter is flowing smoothly. But sudden, dramatic flares and burst signal moments of instability, perhaps when a clump of material crashes onto the neutron star's surface or when the accretion disk undergoes a violent reorganization. By decoding this flickering language of high-energy light, we learn not only about the populations of these dark remnants, but also about the fundamental behavior of matter under the most extreme gravitational stresses imaginable. The serene death of a star can paint the cosmos with ethereal beauty. Within the ancient confines of globular clusters, astronomers have spotted the faint, ghostly glow of planetary nebulae. These are not planets, as their misleading name suggests, but the magnificent final acts of sun-like stars. In their death throes, these stars gently puff away their outer layers into space, creating vast, intricate shells of glowing gas. What makes this discovery so rare and significant is the very nature of the cluster itself. Most of the stars in a globular cluster are ancient red dwarfs, destined to fade slowly, or massive stars that died long ago in violent supernova. A star of just the right mass, one similar to our own Sun, is a relative rarity here. For such a star to be in the precise, brief phase of ejecting its nebula at the very moment we are looking is a cosmic coincidence of incredible fortune. This fleeting window, lasting only a few tens of thousands of years, gives us a direct glimpse into the quiet, inevitable fate that awaits most stars, including our own Sun, billions of years from now. The presence of these nebulae in a cluster tells a powerful story about stellar life cycles in a dense environment. It confirms that even in these ancient swarms, a small population of stars has been living their slow, steady lives, finally reaching their gentle conclusion after more than 10 billion years. Their beautifully sculpted gas, illuminated by the intense ultraviolet light from their exposed hot cores, stands in stark contrast to the cluster's backdrop of ancient, cool red stars. They are like delicate, glowing flowers that bloom for a single cosmic moment in a forest of ancient, gnarled oaks. Studying these objects is a race against time, as their fragile structures are easily disrupted by the cluster's crowded conditions. The gentle pressure from the light of neighboring stars and the subtle gravitational tugs of passing companions can shear and distort the nebula, shaping it in ways we never see in the isolation of our galactic neighborhood. Each one is a unique laboratory, showing us how a star's final breath is shaped by the community it has called home for billions of years. These planetary nebulae are sculpted into shapes we never see anywhere else. Their delicate structures, normally symmetrical rings or gentle spheres, are often twisted into bizarre, asymmetrical forms. Some look like cosmic butterflies with one wing clipped, while others stretch into long, ethereal tendrils. This strange morphology is a direct result of the cluster's crowded environment. The gravitational pull of a nearby binary companion can funnel the dying star's expelled gas into two opposing jets, creating a bipolar nebula. Or the relentless tidal forces from the cluster's core itself can stretch and shear the nebula as it forms, like a strong wind distorting a cloud of smoke. Each distorted shape is therefore a fossil record of the star's immediate neighborhood, a snapshot of the gravitational forces at play during its final 1,000 years. By studying these unique forms, astronomers can calibrate their models of how planetary nebulae form and evolve under extreme conditions. The chemical makeup of this glowing gas adds another layer to the story. These nebulae are rich in the elements forged by the star during its long life: carbon, nitrogen, and oxygen, which are now being returned to the cluster's interstellar medium. In the isolated galactic field, this enriched material simply drifts away, but in a dense cluster, it can be locked in by gravity, potentially becoming part of a future generation of stars or planets. This makes each nebula a brief but vital contributor to the cluster's ongoing chemical enrichment, a final gift from a star that lived and died within the ancient stellar city. The stellar city is not a democracy where all stars are equal. Over billions of years, a relentless sorting process takes place, a gravitational bias that sculpts the cluster from within. This is the strange phenomenon of mass segregation, a slow but inexorable drift where the most massive stars sink toward the center, while the lighter stars are pushed out to the fringes. It is a cosmic version of a centrifuge, separating the heavy from the light through countless gentle gravitational nudges. The mechanism is a subtle force known as dynamical friction. Imagine a massive star moving through a sea of lighter stars. Its powerful gravity creates a slight wake, a denser region of stars trailing behind it. This gravitational wake acts like a drag, pulling back on the massive star and slowly sapping its energy. The heavy star loses speed and momentum, causing its orbit to decay, spiraling it inward toward the cluster's core. Meanwhile, the lighter stars experience the opposite effect, gaining energy from these interactions and being kicked outward to larger, slower orbits. The result is a cluster stratified by weight, with a dense, brilliant core of heavyweights surrounded by a vast, diffuse halo of stellar minnows. This process does not just rearrange the furniture, it fundamentally alters the cluster's destiny, setting the stage for its most dramatic phase, a core collapse. When too many massive stars and stellar remnants crowd into the center, their collective gravity can become unstable. This can trigger a runaway contraction, a gravitational overpacking where the core shrinks to an incredible density. In this state, stellar encounters become fantastically frequent and violent. leading to a burst of collisions, binary formations, and chaotic interactions that can either rejuvenate the cluster with blue stragglers or hasten its eventual dissolution. The entire life cycle of the cluster, its structure and its ultimate fate, is written in this slow, patient segregation of mass, a testament to the unyielding and organizing power of gravity over cosmic time. The ancient cluster Messier 15 is a perfect portrait of this gravitational sorting. Its core blazes with a concentration of massive stars and stellar remnants, a clear sign that mass segregation has run its course over billions of years. This is not a quick process. It unfolds on a timescale known as the relaxation time, the span required for stars to exchange enough energy to settle into this stratified order. For a typical globular cluster, this takes many billions of years, a patient cosmic centrifuge that only now, in the present epoch, is reaching its final state. The consequence of this ordering is a dramatic increase in stellar traffic within the core, transforming it into a bustling hub of cosmic interactions. With so many massive objects packed into such a small volume, the rate of close encounters skyrockets. Stars brush past each other, their gravitational fields intertwining in a complex dance. This heightened traffic directly fuels two of the most dramatic phenomena we find in these clusters. The chance of stellar collisions soars, creating the fiery mergers that give birth to blue stragglers. Simultaneously, the likelihood of stars being gravitationally captured into binary systems increases exponentially. A solitary neutron star can snag a passing red giant. A stellar mass black hole can find a companion to slowly consume, forging the intense X-ray binaries that light up the cluster in high-energy light. The serene structure we see from a distance is therefore an illusion, masking a core that is a hotbed of gravitational encounters, all driven by the slow, relentless sinking of the heaviest objects to the center. The darkness within these clusters may be generating invisible bullets that streak across the galaxy. Astronomers have uncovered evidence that globular clusters are significant sources of cosmic rays, high-energy particles traveling at nearly the speed of light. These are not rays of light, but atomic nuclei, mostly protons, that have been accelerated to energies far beyond anything achievable in our most powerful particle colliders. They constantly bombard the Earth's atmosphere, but their origins have long been a cosmic mystery. The Fermi Gamma Ray Space Telescope provided a crucial clue when it detected faint but persistent gamma-ray glow emanating from several globular clusters. Gamma rays are the most energetic form of light, and they are the telltale signature of cosmic ray activity. Here is how the process works. Inside a cluster, the environment is a maelstrom of powerful stellar winds from massive stars and the expanding shock waves from ancient supernova remnants. These shocks act as natural, colossal particle accelerators. A stray proton or atomic nucleus can get caught in the magnetic fields of these expanding shock fronts, bouncing back and forth like a rubber ball in a cosmic paddle game. With each crossing of the shock wave, the particle gains more energy faster and faster until it is finally ejected as a cosmic ray, a single, invisible projectile flung out into the galaxy. The gamma rays are produced when these newly minted cosmic rays collide with the sluggish, colder gas or the faint light from other stars within the cluster. That collision converts the cosmic ray's immense kinetic energy into a flash of gamma-ray light, a signal that Fermi can detect from across interstellar space. This means these ancient star cities are not just passive collections of stars, they are active cosmic ray factories, their turbulent interiors continuously manufacturing some of the most energetic particles in the universe. This faint gamma-ray glow is a direct window into the invisible storm of particles raging within the cluster. The process that creates it is both violent and elegant. When those ultra-fast cosmic rays, accelerated by shocks, slam into a stray atom of gas or even a photon of starlight, the collision is so powerful it can literally create matter. The energy of the impact transforms into a pair of particles, an electron and its antimatter counterpart, a positron. When these two then meet and annihilate each other, they release their energy in a flash of gamma-ray light. It is a chain reaction of creation and destruction that leaves behind this specific high-energy signature. So the gamma rays are not the cosmic rays themselves, but the brilliant aftermath of their most violent collisions, a ghostly radiance that reveals the presence of these invisible bullets. But what cosmic engine could possibly accelerate particles to such phenomenal speeds within a cluster? One of the prime suspects is the pulsar wind nebula. Imagine the environment around a rapidly spinning neutron star. It is not a quiet place. The pulsar's intense magnetic field and blindingly fast rotation generate a hurricane of high-energy particles, a relentless gale known as a pulsar wind. This wind expands outward, slamming into the slower-moving material around it, creating a massive shock front. This shock acts as a natural particle accelerator of almost unimaginable power, capable of boosting protons and electrons to nearly the speed of light. In the crowded core of a globular cluster where pulsars are common, these pulsar wind nebulae could be the dominant factories for the most energetic cosmic rays. Another potent accelerator might be found in the heart of colliding wind binaries. Picture a system where two incredibly massive stars, or perhaps a massive star and a neutron star, orbit one another closely. Each star blasts out its own powerful stellar wind, a supersonic flow of charged particles. Where these two hurricanes meet, they create a turbulent region of colliding shocks, a chaotic zone of immense pressure and energy. Any particle caught in this cosmic ringer can be accelerated to tremendous energies, again producing the cosmic rays that lead to the gamma-ray glow. The dense environment of the cluster is the key, providing both the powerful engines and the abundant raw material for these collisions. This transforms our view of these ancient structures once more. They are not just cities of stars, but also power plants, generating invisible rivers of high-energy particles that flow out into the galaxy, their presence only given away by the faint, telling glow of gamma light. The constant, slow-motion traffic jam in a cluster's core forges relationships that would be impossible anywhere else. When two stars pass just a little too close, their gravitational fields reach out and grip each other, a process called tidal capture. This is not a head-on collision, but a cosmic handshake that binds the two stars together, creating a new binary system from what was once a fleeting encounter. The key is the immense gravitational pull each star exerts, strong enough to distort the other's shape, stretching them slightly toward one another. This distortion saps energy from their orbits, and instead of flying past, they find themselves locked in a mutual gravitational embrace, destined to circle each other for billions of years. This simple, elegant process is the primary matchmaker for the vast majority of binary stars in these dense stellar cities. It is a fundamental force of social dynamics on a cosmic scale, transforming solitary stars into partners and setting the stage for the most dramatic evolutionary stories in the cluster. The fate of these newly formed pairs depends entirely on their initial dance. If they are born with a wide separation, they may live out long, quiet lives. But if their orbit is tight, their story is just beginning, a prologue to a tale of stellar vampirism, cataclysmic rebirth, or violent transformation. This gravitational matchmaking service is the engine that produces the exotic objects we find scattered throughout the clusters, from the seemingly youthful blue stragglers to the brilliant, high-energy X-ray binaries. The existence of so many binary systems is a direct result of the crowd, a cosmic truth that solitude is a luxury few stars in these ancient cities can afford. These theoretical dances are brought to life through the immense computational power of n-body simulations. Scientists program virtual stars, each with its own mass and velocity, into a digital cosmos and let the laws of physics govern their interactions for billions of simulated years. They watch as these point masses, representing stars, drift through a shared gravitational field, their paths constantly perturbed by near misses and close encounters. The simulations reveal that tidal capture is not a rare event in a dense cluster, but a fundamental and frequent process. For a capture to succeed, the two stars must pass within a critical distance, a delicate balance where their gravitational pull is strong enough to distort each other without triggering a catastrophic collision. The resulting binary system is often born with a distinct signature, a highly eccentric orbit. Instead of a neat circle, the two stars follow a stretched elliptical path, swinging close together before hurtling far apart, a lasting memory of their violent gravitational introduction. This eccentricity is a direct fossil of the capture event, a clue that the binary was not born together peacefully from a single gas cloud, but forged in the chaos of the cluster core. In the real world, the hunt for this evidence leads astronomers to places like the magnificent cluster 47 Tucanae. Here, they search for binary stars with these telltale elongated orbits, a clear observational fingerprint of tidal capture in action. Another signature is found in the stars themselves. The same gravitational tides that bind the stars together can also transfer spin, causing one or both stars to rotate at an unnaturally fast pace. A star that is spinning much faster than its peers is likely a victim of a recent cosmic tango, its rotation sped up by the gravitational pull of a close encounter. By combining the predictions of these sophisticated simulations with precise observations of stellar orbits and rotations, we move from theory to confirmation. We are not just imagining these gravitational handshakes, we are finding their fingerprints scattered throughout the stellar population, proving that the social lives of stars in these ancient cities are shaped by constant, gentle brushes that blossom into lasting partnerships. The light of a star cluster tells a story, but sometimes the pages are missing. When astronomers count the stars in a globular cluster, sorting them by their brightness, they expect to find a predictable distribution, a standard stellar census known as the luminosity function. This function is the cosmic equivalent of taking a head count in a vast city, expecting to find a certain number of children, adults, and elderly citizens based on established birth and death rates. But in some clusters, the census is bizarrely wrong. There are strange deficits or unexpected excesses of specific types of stars. Some clusters have a mysterious shortage of faint, low-mass red dwarfs, the most common stars in the universe. Others show a surprising surplus of stars of a particular, middling brightness. This is not a simple counting error. It is a fundamental mismatch between what our models predict should be there and what we actually see. The stellar population is out of balance, and the reason points to a violent history. One of the most compelling explanations is dynamical erosion. Over billions of years, the relentless gravitational tides of the galaxy and the internal gravitational interactions within the cluster itself can slowly strip away the least massive stars. Think of a bag of mixed marbles being shaken, where the smallest, lightest marbles are the first to bounce out over the edge. These faint red dwarfs, with their relatively weak gravitational grip, are the most vulnerable. They are preferentially ejected from the cluster, tossed out into the galactic halo by gentle but persistent gravitational nudges from their more massive neighbors. This leaves the cluster's luminosity function skewed, missing its faintest, most populous members. But dynamics is not the only suspect. The deficit could be primordial, a relic of the cluster's birth. Perhaps some of these ancient clusters formed in an environment where the gas cloud simply failed to produce as many low-mass stars as we typically see, a different initial recipe for star formation in the early universe. Or, and this is a more shadowy possibility, the missing starlight is not missing at all, but has been hidden. A large population of stellar mass black holes or neutron stars, those dark remnants, could be gravitationally dominating the cluster's core. Their immense, unseen gravity could be actively expelling the lighter stars, dynamically heating the cluster and flushing out the faint red dwarfs over cosmic time. The strange luminosity function is therefore a detective's clue, A deficit of faint stars points to a history of gravitational violence, either from within or from the galaxy outside. An excess of certain stars, on the other hand, could be the signature of that very same dynamical processing. If many stars have been forced into binary systems through close encounters, the resulting stellar collisions and mergers can create new, brighter stars, artificially inflating the numbers in that part of the luminosity function. The light we see, or the light we do not see, is a direct record of the cluster's turbulent life, a story of survival and loss written in the collective glow of its stars. Hubble's deepest stares into these ancient star cities reveal a demographic puzzle. When the telescope meticulously counts and catalogues the stars in a globular cluster, it builds a profile called the luminosity function, a cosmic census of how many bright giants, medium-weight suns, and faint red dwarfs call the cluster home. This census should follow a predictable pattern reflecting the standard way stars are born, but in cluster after cluster, the numbers are strangely skewed. There is a mysterious and consistent shortage of the faintest, lowest mass stars. It is as if a vast city had all its neighborhoods but was missing nearly all its children. This missing light points to a deep and ongoing transformation within these clusters. One of the most compelling explanations is a process of slow evaporation. Over billions of years, the gentle but relentless gravitational tides from the host galaxy, combined with the constant gravitational nudges from stars within the cluster itself, act like a cosmic sieve. The stars with the weakest gravitational grip, the lightweight red dwarfs, are the most easily shaken loose. They are gradually stripped away, ejected from the cluster to wander alone in the dark galactic halo. The cluster is slowly bleeding its smallest citizens, leaving behind a population skewed toward heavier, brighter stars. But evaporation is not the only suspect. Another interpretation suggests the missing starlight is an illusion created by the cluster's dark past. What if the deficit of faint red dwarfs is balanced by a vast, unseen population of stellar corpses? White dwarfs, the dense Earth-sized cores left behind by sun-like stars, and neutron stars, the even more massive remnants of supernova explosions, emit very little light. If a globular cluster contains a huge number of these dark remnants, their collective gravity would dominate the cluster's dynamics, but they would not show up in the optical census. Their powerful gravitational influence could even be the very engine that accelerates the evaporation of the low-mass stars, solving the mystery by pointing to two intertwined causes. Hubble's deep fields force us to see these clusters not as static museums, but as dynamic systems undergoing a constant, slow-motion purification, where gravity is patiently sorting the population, deciding which stars remain and which are cast out into the eternal night. Our own galaxy's ancient clusters are just one chapter in a much larger cosmic story. The true scope of their mystery unfolds when we look beyond the Milky Way to the vast collections of globular clusters orbiting other galaxies. These extragalactic systems hold up a mirror to our own, and the reflection is often startlingly different. Giant elliptical galaxies, in particular, are surrounded by thousands of these stellar swarms, far more than the few hundred that orbit our spiral home. When astronomers began to study these distant clusters in detail, they noticed a profound and consistent pattern. Their colors were not random. Instead of a smooth gradient, the clusters fell into two distinct groups, a phenomenon known as color bimodality. One group shone with a distinct reddish hue, while the other gleamed with a brilliant bluish-white light. This is not merely an aesthetic difference, it is a fundamental clue written in the language of stellar chemistry. The color of a star cluster is a direct indicator of its metallicity, the amount of heavy elements it contains beyond hydrogen and helium. The red clusters are metal-rich, their stars enriched with the forged elements of countless stellar generations. The blue clusters are metal-poor, pristine relics from the early universe, much like the oldest clusters in our own halo. This stark division tells a story of two separate epochs of creation. two distinct waves of cluster formation in the galaxy's violent history. The blue metal pore clusters are the ancient pioneers, forming first during the initial chaotic collapse of the galaxy itself, or in the primordial building blocks that merged to create it. The red, metal-rich clusters came later, born from the gas that had been polluted and enriched by billions of years of stellar life and death within the bustling galaxy. In a spiral galaxy like our own, we see a hint of this, with redder clusters concentrated in the dusty disk and bluer ones in the sparse halo. But in giant ellipticals, the bimodality is overwhelming, a clear fossil record of a past built through colossal mergers and relentless, ongoing star formation. This simple observation of color forces us to abandon the idea of a single, universal recipe for globular clusters. Their properties are a direct reflection of the galaxy they call home, a living diary of its most turbulent and formative events. These ancient stellar swarms act as brilliant tracers, illuminating the violent construction of the cosmos itself. When we study the globular clusters orbiting distant galaxies, we are reading a history book written in starlight, a chronicle of galactic cannibalism and growth. The powerful infrared eyes of the James Webb Space Telescope are now peering deeper into this history, analyzing the precise chemistry of clusters in galaxies billions of light-years away. The distinct red and blue populations are not just a static fact, they are a dynamic record. The metal pore blue clusters are the cosmic fossils, the original inhabitants of the small, primordial galaxies that existed in the early universe. The metal-rich red clusters are the newcomers, forged later in the intense star-forming regions triggered by galactic collisions. When two galaxies merge in a cataclysmic dance, their gravitational embrace compresses vast clouds of gas, igniting a firestorm of new star birth. From this enriched, turbulent gas, new globular clusters are born, their stars already polluted with the heavy elements from previous generations. This means that by simply counting the ratio of red to blue clusters around a giant elliptical galaxy, we can estimate its violent past, how many smaller galaxies it has consumed over billions of years. The clusters are the enduring confetti from a cosmic party that ended long ago, still swirling in the aftermath. This reveals that a galaxy's entire evolutionary path is mirrored in the population of its orbiting star clusters. A quiet, isolated galaxy might possess only old blue clusters. A galaxy built from a series of violent mergers will be surrounded by a rich mix of both red and blue, a layered archaeological record of its tumultuous assembly. The environment is everything, shaping not just the galaxies but the very nature of their stellar attendants. In the dense, violent core of a galaxy cluster, where interactions are frequent and brutal, we find the most extreme examples. Here, the gravitational tides are so fierce that they can rip entire globular clusters from their host galaxies, flinging them out into the blackness of intergalactic space. These are the rogue clusters, orphaned stellar cities drifting alone in the vast voids between galaxies. They are cosmic ghosts, their light a faint echo of a home they left behind eons ago. Finding them is a testament to the sheer violence of the environments that created them, and their isolated existence raises a profound question. Could a planet orbiting a star in such a cluster ever conceive of a galaxy, when its entire universe is a single, dense ball of stars against an eternal, empty night? These intergalactic wanderers are the ultimate survivors, their continued existence proving the resilience of gravity's bond, even when severed from the galactic heart that gave them birth. These silent rhythms of the cosmos are captured by an invisible network spanning the galaxy. Within the dense hearts of globular clusters, astronomers have synchronized the ticking of multiple millisecond pulsars, creating a pulsar timing array. Each pulsar is a celestial metronome of incredible stability, its radio pulses arriving on Earth with a predictability that rivals our most advanced atomic clocks. By monitoring an array of these pulsars across different clusters, scientists can detect the most subtle distortions in the fabric of spacetime itself. The goal is to catch the faint, rolling passage of low-frequency gravitational waves, the kind generated not by stellar mass black holes, but by the slow, cosmic dance of supermassive black hole binaries at the centers of distant galaxies. These waves are not the sharp chirps detected by LIGO and Virgo. They are a continuous, universe-spanning hum, a background rumble left over from countless mergers throughout cosmic history. As these long wavelength gravitational waves wash over the galaxy, they minutely alter the distances between Earth and the pulsars. When a wave passes through, it briefly compresses space in one direction and stretches it in another. This tiny distortion causes the rhythmic pulses from some pulsars to arrive slightly early, while others are delayed by a minuscule amount. The effect is incredibly subtle, a timing shift of just a few hundred nanoseconds over years of observation. It is like trying to detect a change in the distance from New York to Los Angeles by less than the width of a human hair, but by cross-referencing the timing variations from dozens of these precise pulsar clocks, a pattern emerges from the noise. The coordinated drift reveals the direction, frequency, and amplitude of the gravitational waves bending our galactic neighborhood. This transforms the entire globular cluster system into a colossal interstellar observatory, one with a baseline of thousands of light years, sensitive to the slowest, most profound rhythms of the universe. It allows us to listen for the collective groan of all the supermassive black holes in the universe, spiraling toward their eventual mergers, a sound that has been traveling through the cosmos since before these very clusters were born. This coordinated listening effort spans the entire globe, uniting radio telescopes from North America, Europe, and Australia into a single planet-sized instrument. These international collaborations, like the International Pulsar Timing Array, pool their data to achieve a sensitivity impossible for any single project. They are not listening for a single event, but for a background hum, a chorus of low-frequency gravitational waves that should perpetually wash through our galaxy. The key to this search lies in the timing residuals, the tiny discrepancies between when a pulsar's pulse is expected to arrive and when it actually does. If these delays were random for each pulsar, it would simply be noise, but if a consistent pattern of correlation is found across the entire array, a specific signature where some pulsars are delayed while others are advanced in a coordinated way, it is the unmistakable fingerprint of a passing gravitational wave. This background rumble is thought to be generated by the cosmic dance of supermassive black hole binaries, pairs of monsters weighing billions of suns, orbiting each other at the centers of distant galaxies. As they spiral inward over millions of years, they fill the universe with these long wavelength ripples. Detecting this signal would open an entirely new window onto the most massive objects in the cosmos, allowing us to census the population of these binary behemoths and understand their role in galaxy evolution. Beyond that, it provides a fundamental test of gravity itself. Does Einstein's theory of general relativity hold true in this regime of unimaginably strong fields and cosmic scales? Or will the precise timing of these pulsars reveal a subtle deviation, a hint of new physics that could rewrite our understanding of space-time? The ancient, steady beats from these globular clusters are tuning forks for the universe, and we are just beginning to hear the music they are helping us play. Deep within the infrared glow of these clusters, a ghostly signature flickers. Astronomers have detected unidentified infrared emissions, a mysterious light that does not match the expected output of any known star or simple dust particle. This enigmatic signal presents itself as a set of specific wavelengths, a chemical barcode we cannot yet fully decipher. The leading suspect is a family of complex carbon-based molecules known as polycyclic aromatic hydrocarbons. These are not living organisms, but sprawling, sooty molecules made of interlocking rings of carbon and hydrogen, essentially the same compounds found in the smoke from a candle flame or the char on a piece of grilled food. Finding them in the pristine environment of a globular cluster is like finding a fingerprint of a city dweller on a remote, uninhabited mountain peak. It is entirely out of place. Their presence would be a profound puzzle. These ancient clusters are supposed to be devoid of the raw materials needed to create such complex dust, having long ago used up or expelled the gas required for new chemical processes. So how did these carbon compounds get there? One possibility is that they are the frozen ashes of older generations of stars. As ancient red giants and asymptotic giant branch stars neared the end of their lives, they may have blown out winds rich in carbon, which then condensed into these complex molecules in the cold, dark spaces between the stars. This suggests a hidden, ongoing chemical life within the cluster, a slow cycle of creation that continues long after the main fireworks of star formation have ceased. Another, more radical idea is that these emissions are not from hydrocarbons at all, but from a completely new form of carbon-based dust, perhaps even nanodiamonds or other exotic materials forged in the extreme environments around dying stars. This unidentified glow forces us to reconsider the very nature of interstellar dust and the chemical legacy that stars leave behind, a faint, warm breath of complex molecules lingering in the cosmic dark. The faint infrared glow from these clusters is a message waiting to be decoded, and the James Webb Space Telescope is the perfect instrument to read it. Its powerful infrared eyes are uniquely suited to pierce through the cosmic dust that can obscure visible light, seeing the warm emissions that other telescopes miss. Where Hubble sees the brilliant points of stars, Webb sees the gentle, diffuse heat between them, the realm where these mysterious chemical signatures reside. It can split that infrared light into an exquisitely detailed spectrum, revealing not just the presence of these complex molecules, but their exact chemical structure and how they are being excited. This is like moving from a blurry photograph of a distant city to a detailed analysis of the very smoke rising from its chimneys. Webb's data could finally confirm if the signal comes from sprawling carbon molecules, the polycyclic aromatic hydrocarbons, or if it points to something even more exotic, like the glittering signature of nanodiamonds forged in the atmospheres of dying stars. This analysis is not just about identifying a substance, it is about uncovering the hidden life cycle of matter within these ancient cities. One of the prime suspects for producing this dust is a specific late stage of stellar life, the asymptotic giant branch stars. These are aging, bloated giants in their final act, pulsating rhythmically and blowing their outer layers into space in slow, dense winds. These winds are rich with newly forged carbon, and as they expand and cool, that carbon can condense into sooty particles and complex molecules, seeding the cluster's interior with a faint, warm dust. Webb can observe this process in action, watching these stellar elders exhale their dusty remains into the void. But there is another, more unsettling possibility that Webb is investigating: external contamination. Could this dust have an origin outside the cluster itself? As the cluster plows through the halo of its host galaxy, it might be sweeping up interstellar material, dust that was forged in other, younger stellar environments and now drifts as cosmic pollution into the pristine cluster. If Webb's spectral analysis shows a chemical mix that does not match what the cluster's own stars could produce, it would be evidence that these ancient systems are not entirely closed. They are permeable, collecting the galactic debris of their long journeys, their purity subtly compromised by the environment they travel through. This turns the cluster from a sealed fossil into an active participant in the galactic ecosystem, one that both creates its own dust and gathers the ashes of others. A silent, relentless drag is pulling at the ancient star cities orbiting our galaxy. This force, known as dynamical friction, is not a wind or a tide of water, but a gravitational phenomenon born from the galaxy's own invisible halo of dark matter. As a globular cluster travels through this vast, diffuse cloud, its immense gravity tugs on the dark matter particles and the sparse, old stars that make up the halo. The cluster creates a slight, dense wake behind it, a gravitational overdensity that acts like an anchor. This wake pulls backward on the cluster, steadily sapping its orbital energy. The effect is a slow, cosmic braking maneuver that can only end one way, with the cluster losing speed and spiraling inexorably inward toward the galactic center. This is not a fast process. It unfolds over billions of years, a patient and inevitable decay that dictates the ultimate fate of these stellar systems. The consequences are profound. A cluster on a plunging orbit that brings it too close to the galactic bulge will experience gravitational tides so fierce they can tear it apart in a single close pass. A cluster on a wider orbit might spiral inward more gently, its stars gradually stripped away over many orbits until it is completely dissolved, its stars scattered into the galaxy's general population. This dynamical friction is the reason we see so few globular clusters near the bustling core of the Milky Way. The region is a gravitational graveyard where these ancient structures cannot long survive. Their survival depends entirely on their initial trajectory, a cosmic lottery drawn at their birth that determines whether they will live out their lives in the quiet halo or be consumed by the galaxy's hungry heart. This process is not just a death sentence, it is a powerful shaping force. It explains the very distribution of clusters we see today, with most of them orbiting at a safe distance from the center, while a few brave or unlucky souls are caught in the final stages of their long inward spiral. Their current positions are a map of their past interactions, a story of gravitational resistance written across the galactic sky. The clock on orbital decay ticks with excruciating patience. For a typical globular cluster, the spiral toward galactic destruction takes many billions of years, a timescale that dwarfs the entire history of life on our planet. This slow-motion fate is dictated by the cluster's initial orbit, a cosmic starting position set during its formation that determines its entire future. A cluster born on a wide, circular path far from the galactic center may feel this drag only weakly, destined to orbit peacefully in the halo for eons longer than the current age of the universe. But a cluster on a more elliptical, plunging orbit is living on borrowed time. Each close pass by the dense galactic bulge saps a little more of its orbital energy through that relentless dynamical friction, tightening its path and ensuring its next approach will be even closer. The process accelerates as the cluster sinks lower, a gravitational feedback loop that can only end in dissolution. We see this dramatic future playing out in systems like the magnificent Omega Centauri. This giant cluster, one of the largest we know, orbits closer to the galactic center than many of its peers. Its immense mass creates a stronger gravitational wake, hastening its orbital decay. Some astronomers speculate that Omega Centauri is not a true globular cluster at all, but the stripped core of a dwarf galaxy that ventured too close to the Milky Way long ago. If that is true, then its current slow spiral inward is just the final chapter of a disintegration that began billions of years ago. It serves as a stunning preview of what may happen to other massive clusters, a glimpse of a future where they are torn apart, their stars scattered to fuel the growth of the galactic bulge itself. This gravitational erosion does not always lead to a clean absorption. Often, a cluster is simply disrupted before it reaches the center. As it plunges through the galactic plane, the differential tidal forces can stretch it beyond its breaking point. Stars are peeled away from the outer layers, forming long, faint streams that precede the main body like cosmic forewarning. The cluster does not die in a single, brilliant flash, but fades away like a piece of chalk crumbling in your hand, its constituent stars returning to the anonymous population of the galaxy. This means the brilliant globular clusters we see today are the survivors, the fortunate ones whose orbits have kept them safe from the galaxy's most violent tides. Their continued existence is a testament to a delicate balance between their own binding gravity and the relentless pull of the galaxy they call home. How many of these ancient cities have we already lost, their stars now indistinguishable from the rest of the galactic halo? Their silent, patient decay reminds us that even the most enduring cosmic structures are temporary, and that the galaxy itself is a dynamic, ever-changing ecosystem, constantly consuming its oldest constituents to build its future. The dense heart of a globular cluster may hide a relic from the universe's first second. Among the stellar mass black holes formed from dead stars, there could be something far older and more exotic, a primordial black hole. These are not the products of stellar collapse, but hypothetical objects thought to have been born in the extreme density and turbulence following the Big Bang itself. They would be fossils of the cosmos's most violent infancy, and some theories suggest they could be hiding within these ancient stellar swarms. Their presence would solve a persistent puzzle, the precise, rapid movements of stars in certain cluster cores that sometimes seem to demand more central mass than we can account for with visible stars or even the expected population of stellar remnants. An ancient, heavy primordial black hole could be that missing gravitational anchor, influencing the motions of thousands of stars without emitting a single photon of light. This idea pushes beyond conventional stellar evolution, suggesting that the invisible architecture of a cluster might be built not just from dead stars, but from the leftover knots of creation itself. If they exist, these primordial black holes could also represent a fraction of the universe's mysterious dark matter, their collective gravity bound up in the cluster's core. Detecting such an object is a monumental challenge, as it would be indistinguishable from a stellar mass black hole through most observations. The hunt relies on finding a cluster with a gravitational signature that is too compact, too massive, and simply too old to have been formed by the death of a star that belonged to the cluster. It would be a ghost from a time before stars existed, a silent passenger on a journey that began when the cosmos was just a seething, newborn sea of energy. Hunting for these cosmic phantoms requires reading the faintest whispers of gravity's influence. The primary method remains gravitational microlensing, a patient watch for the brief, telltale brightening of a distant star. If a primordial black hole drifts perfectly between that star and our telescopes, its gravity will act as a tiny lens, focusing the starlight and causing a sudden, temporary flare. The duration of this flash is key. A longer brightening suggests a heavier lens, potentially revealing the mass of the invisible object passing by. Yet, this technique is a game of cosmic chance, relying on a perfect and fleeting alignment across thousands of light years. Another promising avenue listens for the echoes of violent encounters. When a primordial black hole merges with a neutron star or another black hole within the cluster, it would release a storm of gravitational waves, ripples in space-time detectable by observatories like LIGO and Virgo. The unique mass of a primordial black hole, potentially lighter or stranger than its stellar-born cousins, would leave a distinct signature in the gravitational wave signal, a fingerprint of its ancient origin. The most subtle clue, however, comes from the collective motion of the cluster's stars themselves. Precise tracking of stellar velocities, especially near the core, can reveal the gravitational pull of an unseen central mass. If the kinematics point to a compact, heavy object that seems too ancient to have formed from a cluster star, it becomes a prime suspect for a primordial black hole anchor. Despite these sophisticated searches, the evidence remains elusive, constrained by the sheer difficulty of the task. Current observations have ruled out the possibility that large numbers of planet-mass primordial black holes make up the dark matter in these clusters, but the door remains open for a smaller population of heavier ones hiding in plain sight within the stellar dance. Their continued absence is itself a profound piece of data, narrowing the possible conditions of the universe's explosive birth and challenging us to devise ever more clever ways to listen for the silent ghosts of creation. These ghostly rivers of stars are the final echoes of long-lost stellar cities. Across the vast, dark halo of our Milky Way, astronomers have mapped faint, shimmering streams of stars, tracing graceful arcs that stretch for thousands of light years. These are not random formations, they are the unraveled remains of globular clusters that were completely torn apart by our galaxy's immense gravity. Each stream is a cosmic crime scene, and the evidence points to a violent, slow-motion dismemberment that took billions of years. As a cluster orbits the galaxy, the difference in gravitational pull between its near side and its far side creates a stretching force, a tidal pull that relentlessly tugs stars away. The cluster's own gravity fights to hold on, but over countless orbits, it loses the battle. Stars are gradually stripped from the outer layers, first in a trickle, then in a steady flow, until the cluster is reduced to a single, brilliant river of stars, a ghost of its former self. These streams are more than just beautiful relics, they are the ultimate fossils, preserving the orbital DNA of systems that no longer exist. By tracing the path of a stream like the one from the disrupted cluster known as the Helmi stream, scientists can rewind the cosmic clock. They can calculate the precise orbit the parent cluster followed, and from that, deduce the gravitational forces it experienced throughout its long history. This allows them to map the distribution of dark matter in our galaxy's halo with incredible precision, because it is the invisible dark matter that primarily dictates how these streams twist and turn through space. Every kink, every gap, every subtle bend in a stellar river is a clue, a record of a past close encounter with a smaller galaxy, a clump of dark matter, or another cluster. These streams are therefore a living archive, a dynamic history book that chronicles the Milky Way's growth through cannibalism and merger, written in the scattered light of its most ancient stars. Gaia's precision has turned a faint cosmic whisper into a clear, articulate voice. This space observatory is not merely taking pictures, it is charting a three-dimensional movie of our galaxy, measuring the positions, distances, and motions of over 1 billion stars. Before Gaia, stellar streams were often just smudges of light, statistical hints in star counts. Now we can watch individual stars moving in unison, tracing the ghostly orbital path of their parent cluster as if watching a river flow in slow motion. By tracking these stars back through time, astronomers perform a kind of cosmic genealogy, identifying streams that share a common origin and reuniting stellar families torn apart billions of years ago. This has revealed a hidden history of carnage. The number of distinct streams now catalogued suggests our galaxy's halo is a galactic graveyard, littered with the remains of hundreds of globular clusters that no longer exist. The Milky Way was a far more prolific cluster factory in its youth, and it has been systematically consuming its own creations ever since. The types of clusters that were destroyed also tell a story. The streams reveal that smaller, less massive clusters were the most vulnerable, easily shredded by galactic tides. Their widespread dissolution explains why the globular clusters we see today are mostly the big, dense survivors, the ones with enough gravitational fortitude to withstand the galaxy's pull. This transforms our understanding of the galactic ecosystem. We are not looking at a complete set of ancient relics, but a biased sample of the toughest ones that endured. The graceful streams are therefore more than just fossils. They are a lost census, revealing a vibrant, diverse population of star clusters that once filled our galaxy, a population now only visible in the faint, unraveled threads of its final members. A faint, persistent radio hum surrounds some of the oldest objects in the sky, while powerful telescopes like the Chandra X-ray Observatory revealed brilliant point sources like pulsars and X-ray binaries. Another signal has emerged from the void, one that is far more diffuse and enigmatic. This is the strange case of unusual radio continuum emissions, a soft, all-encompassing radio glow that envelops entire globular clusters. Unlike the sharp, rhythmic pulses from a neutron star, this emission is a smooth, continuous whisper, a background hiss that cannot be traced to any single star or known object. It is not the focused beam of a lighthouse, but the uniform fog blanketing an entire coastline. This faint radio light is a form of synchrotron radiation, the signature of electrons spiraling at nearly the speed of light through vast magnetized fields. Its presence suggests that these ancient clusters are threaded with invisible magnetic structures and are continuously generating a sea of high-energy particles. The question is, what cosmic engine could possibly be responsible for this persistent cluster-wide emission? The known pulsars within the clusters are not enough to account for it. Their energy is too localized. This points to a larger, more integrated process. One possibility is a vast, diffuse population of cosmic rays, electrons accelerated to fantastic speeds by the combined shock waves of ancient supernova and the powerful winds from countless stars. These particles, trapped by the cluster's magnetic field, would spiral for eons, emitting this faint radio hum as they travel. Another, more exotic idea is that the clusters themselves possess a large-scale, organized magnetic field, a relic from their formation that has persisted for billions of years. This magnetic architecture could be accelerating particles across the entire system, creating a unified radio aura. This gentle radio whisper forces us to see these clusters not just as collections of stars, but as unified entities with their own invisible atmospheres of magnetism and high-energy physics, a hidden dimension of activity that has been quietly broadcasting its presence since the universe was young. Low-frequency radio waves offer a new way to listen to the ancient whispers of these clusters. Traditional telescopes see the brilliant points of starlight, but instruments like LOFAR, the low-frequency array, are tuned to a much deeper register. They detect radio waves with wavelengths as long as a city block, a part of the spectrum that can pass through cosmic dust and reveal the faint, extended structures that other observatories miss. When LOFAR turns its thousands of small antennas toward a globular cluster, it is not just looking for stars, it is mapping the invisible architecture of magnetic fields and tracing the paths of the most energetic electrons. This low-frequency view is crucial because the synchrotron radiation from these high-energy particles is brightest at these long wavelengths. The faint radio glow that seemed like a uniform fog to other telescopes is now resolving into intricate patterns, revealing how magnetic fields are woven through the entire stellar city and where vast, gentle shocks are still accelerating particles to nearly the speed of light. The future of this exploration lies with the Square Kilometre Array, or SCAR, a project that will be the largest radio observatory ever built. Its unprecedented sensitivity and resolution will allow it to create a high-definition movie of this radio universe. The SKA will not just detect the cluster's magnetic field, it will trace its individual lines of force, showing how they are twisted and amplified by the turbulent motions of stars and the powerful winds from pulsars. It could reveal the presence of previously invisible shock waves, the lingering echoes of supernova that exploded billions of years ago, which are still acting as powerful particle accelerators. This may solve the mystery of the radio hum, identifying whether it comes from a diffuse sea of cosmic rays or from discrete, powerful engines hidden in the dark. The ultimate promise of these telescopes is to discover entirely new phenomena. The ultra-sensitive ears of the SKA might pick up the faint radio signature of a primordial black hole as it subtly distorts the surrounding magnetic field. Or it could detect the unique radio burst from a magnetar starquake in a frequency range we have never before been able to probe. We are on the verge of hearing the full symphony of these ancient clusters, a complex composition played not in light, but in the long, low notes of magnetic force and relativistic particles. The chemistry of a star can betray a history of cosmic theft. Among the ancient stellar populations of globular clusters, astronomers have identified stars that are bizarrely rich in helium, an element that should have been largely locked away in their cores. These are not the red giants or blue stragglers we have come to expect, but stars whose outer atmospheres have been contaminated, altering their very essence and their path through life. A star with an overabundance of helium in its outer layers burns at a higher temperature for its mass, appearing bluer and brighter than its peers. It is a stellar imposter, a star that looks younger and more massive than it truly is, all because of its peculiar chemistry. So how does a star acquire this forbidden abundance? The evidence points to two dramatic scenarios, both rooted in the intimate, crowded environment of the cluster. The first is a story of stellar pollution. In the cluster's youth, the most massive stars of the first generation raced through their lives and exploded, scattering their helium-rich ashes into the surrounding gas. When the second generation of stars formed from this enriched material, they were born with this helium boost already woven into their fabric. They are the inheritors of a chemical legacy, carrying the elemental fingerprint of their long-dead ancestors. The second scenario is more immediate and violent. It involves a binary system where one star, nearing the end of its life, swells into a red giant. Its outer layers, brimming with helium fused deep in its core, become gravitationally vulnerable. A nearby companion star can then siphon this helium-rich material directly, accreting it onto its own surface. The receiving star is fundamentally transformed, its outer layers now polluted with this fresh fuel, effectively hitting the reset button on its evolution. This stellar cannibalism creates a helium-rich star not from birth but from a late-life feast. This dramatic transformation has profound consequences. A helium-enriched star will evolve differently, following a unique track on the Hertzsprung-Russell diagram. It may skip certain evolutionary phases entirely or blaze through them at an accelerated pace, its life story rewritten by the chemistry of its surface. This forces astronomers to recalibrate their models of stellar aging within clusters, as a significant population of these imposters can skew our understanding of the cluster's true age and history. These strange stars are a testament to the complex social lives of stellar citizens. They remind us that a star's destiny is not written solely at its birth, but can be dramatically altered by the company it keeps and the cosmic inheritance it receives. This helium enrichment fundamentally rewrites a star's life story. A star polluted with extra helium burns hotter and brighter than a normal star of the same mass, but this vitality comes at a steep price. It lives a far more extravagant life, consuming its hydrogen fuel at a prodigious rate, which leads to a significantly shorter lifetime. This is not a gentle aging process, but a rushed and dramatic evolution that pushes the star into bizarre and unexpected states. The most striking consequence appears on the horizontal branch, a specific stage of stellar life where old, sun-like stars burn helium in their cores. In a normal cluster, these stars form a predictable, gently curved line on the Hertzsprung-Russell diagram. But in clusters with helium-enriched populations, something strange happens. The horizontal branch does not just curve, it curls back on itself, creating a sharp kink populated by stars that are far hotter and bluer than they have any right to be. These are the blue hook stars, stellar anomalies that appear to hook backwards on the diagram, defying the standard path of evolution. How can a star become bluer and hotter as it ages, seemingly moving backwards in its life cycle? The answer lies in the star's internal chemistry. For these helium-rich stars, the drama unfolds deep within their envelopes. Under extreme conditions, the nuclear fusion process can become unstable, triggering a frantic and sudden mixing of the star's interior. This violent churning dredges up fresh carbon from the core and brings it to the surface where it acts like a cosmic sunscreen. This carbon blanket allows the star to radiate its energy more efficiently, causing it to shrink and heat up even further, creating that dramatic blue hook in its evolutionary path. It is a stellar metamorphosis, a late-life transformation driven by an unstable nuclear furnace and an atmosphere that should not exist. This single class of star forces a complete overhaul of our stellar models. It proves that a star's surface composition is not always a fixed relic of its birth, but can be dynamically altered by violent internal processes we are only beginning to understand. The blue hook is a flag planted in the charts of stellar evolution, marking a territory where the old, simple rules no longer apply, and where the crowded, complex environment of a globular cluster writes its own strange laws of stellar life and death. The silent tremors from these ancient star cities are building into a cosmic hum. Every time two black holes or neutron stars spiral together and merge in the dense heart of a globular cluster, they do not just create a single, sharp chirp of gravitational waves. They send out a ripple in the fabric of space-time, a vibration that travels across the universe. Now, imagine not one, but thousands of these mergers happening across millions of galaxies all throughout cosmic history. The combined effect is a persistent, low rumble known as the stochastic gravitational wave background. It is a chorus of countless collisions, a universe filled with the faint, overlapping echoes of these violent unions. This background is not a clear signal from a single event, but a collective murmur like the sound of a distant, roaring crowd heard from miles away. Globular clusters are one of the primary factories for this cosmic noise. Their uniquely crowded conditions make them perfect breeding grounds for the binary black holes and neutron stars that create these waves. In the serene galactic suburbs, such violent partnerships are rare, but inside a cluster, gravitational encounters are a constant fact of life, pairing up stellar corpses into tight, fatal dances. These clusters are relentless engines, continuously producing the merging binaries that contribute to this universal hum. Observatories like LIGO, Virgo, and Cagra are now tuning their incredible sensitivity to listen for this background. They are not searching for a single, distinct chirp anymore, but for a correlated static that appears across their multiple detectors. It is an immensely difficult task, like trying to hear a single conversation in a stadium packed with screaming fans. But by cross-referencing the data from these facilities across the globe, scientists are beginning to pick out the first hints of this collective rumble. Detecting it provides a unique window into the population dynamics of these clusters. The specific frequency and amplitude of the hum will tell us how many of these compact binary mergers are happening and what their typical masses are. This is a direct census of the invisible inhabitants of globular clusters, a way of counting the stellar mass black holes and neutron stars without ever seeing their light. The gravitational wave background is the integrated voice of all these dark remnants, a story of cosmic violence and partnership told not in light, but in the subtle shivering of space-time itself. These simulated stellar cities tell a story written in gravitational waves. By running countless computer models, a process called population synthesis, astronomers can estimate the rate at which black holes and neutron stars merge within these dense environments. They create a virtual universe, seeding it with millions of stars according to the known rules of stellar evolution and dynamics, and then let the simulation run for billions of virtual years. The results are startling. A single, massive globular cluster might produce a stellar mass black hole merger once every few 100 million years. Across the entire population of clusters in a galaxy, this adds up to a steady, persistent drumbeat of cosmic collisions. Each of these simulated mergers produces a specific gravitational wave signal, a chirp whose pitch and duration reveal the masses of the colliding objects. By adding together the predicted signals from all the clusters in the observable universe, scientists generate a forecast, a detailed prediction of the gravitational wave background hum that observatories like LIGO and Virgo should be able to hear. This is more than just a theoretical exercise. It is a crucial tool for interpreting the real data we are now collecting. When a gravitational wave observatory detects a signal, the first question is, where did this come from? The population synthesis models provide the answer. A merger between two black holes, each around 30 times the mass of our Sun, is a classic signature of a globular cluster origin. In the isolated galactic field, stars rarely become so massive, but in the frantic environment of a cluster, black holes can grow through repeated mergers, building up heft over time. The models also predict the distribution of these masses, telling us how common these heavy pairs should be compared to lighter ones. This allows us to use the gravitational wave signals as a cosmic census, taking a roll call of the dark remnants hidden within these ancient star swarms. Every chirp we detect either confirms our models of cluster dynamics or forces us to rewrite them, offering a direct line into the invisible, violent heart of the cosmos's oldest stellar cities. A star's path should be a predictable arc, a gentle curve defined by the cluster's collective gravity. Yet when astronomers tracked the individual journeys of thousands of stars within these ancient cities, they found subtle rebellions. Precise measurements from observatories like Gaia revealed strange proper motion anomalies, tiny but significant deviations from the expected stellar paths. This is not the grand, whirling dance of stars around an intermediate mass black hole, but something far more subtle, a faint trembling in the cosmic choreography. It is as if invisible hands are gently nudging these stars, altering their trajectories in ways that cannot be explained by the pull of their luminous neighbors alone. The very fabric of the cluster's gravity seems to be textured, lumpy with unseen influences. These minute deflections are the ghosts in the machine, the gravitational fingerprints of masses we cannot see. One compelling explanation points to a hidden population of stellar mass black holes and neutron stars drifting like dark icebergs through the stellar sea. Their concentrated gravity, though invisible, would exert a constant, subtle pull on passing stars, tweaking their proper motions over time. Another, more exotic possibility is that we are seeing the effect of dark matter substructure within the cluster itself. While globular clusters as a whole appear devoid of dark matter, it is possible that small, dense clumps of it survived from the early universe, lingering within the cluster and warping the paths of nearby stars with their invisible mass. Each anomalous motion is a clue, a single thread in a web of gravitational intrigue, forcing us to map the cluster not by the light we see, but by the silent, persistent tug of the darkness we cannot. Gaia's map is so precise it can track the drift of a star over decades, as if measuring the growth of a tree from 1,000,000 miles away. This incredible data is the key to isolating those subtle stellar path deviations from the predictable flow of cluster motion. Astronomers begin by charting the expected trajectory for every star, a smooth path dictated by the cluster's overall gravitational field. Then they search for the tiny discrepancies, the stars that are ever so slightly ahead or behind, or moving at a minute angle to the expected flow. These are the proper motion anomalies, the whispers of unseen mass, but the signal is incredibly faint, and the first task is to rule out the obvious culprit, the external pull of the galaxy itself. Our entire Milky Way exerts a tidal force on the cluster, stretching it and subtly altering stellar paths in a predictable, large-scale pattern. Scientists use sophisticated models to subtract this galactic tide, digitally removing the background rumble of the entire galaxy's gravity. What remains are the internal anomalies, the small-scale deflections that must be caused by something within the cluster's own boundaries. This refined data reveals a hidden landscape of mass. The anomalies are not random. They cluster in specific regions, often in the densely packed core, mapping out the locations where invisible, massive objects are gravitationally tugging on their luminous neighbors. By analyzing the precise direction and magnitude of these stellar path deviations, astronomers can perform a kind of cosmic tomography, reconstructing the distribution of dark mass within the cluster. It is a gravitational autopsy, using the faint trembling of starlight to reveal the bones of the system, the compact remnants, and perhaps even those elusive dark matter clumps that shape the cluster from within. Our journey through these 50 discoveries reveals a universe within a universe. These ancient star clusters are not the simple fossils we once believed them to be. They are dynamic cities, home to stellar rebirths, hidden black holes, and chemical mysteries that rewrite the story of cosmic evolution. They have challenged our most fundamental measurements, from the age of the cosmos to the very nature of dark matter. They have proven to be factories for the most energetic particles and the most violent gravitational waves. From the paradox of stars older than time to the silent drift of dark remnants, every strange finding peels back a layer, showing us that the cosmos is far more intricate, connected, and wondrous than we ever dreamed. These clusters are not just distant points of light. They are active participants in the grand narrative of the universe, holding secrets about our past and clues to our future. We would love to hear which of these 50 discoveries captured your imagination the most. Was it the stellar age paradox, the blue stragglers cheating death, or the ghostly streams of unraveled clusters? Let us know in the comments and subscribe to continue exploring the deepest mysteries of space together.